beyond Neptune, past the icy Kuiper belt, there's a region of space we've never explored directly. It's the edge of our solar system, where the sun's influence begins to fade and the pull of other stars slowly takes over. The big question is simple. Will humanity always stay close to the sun, or will we one day push further, leaving our solar system and setting out into the galaxy? Before we begin, like the video and comment below where in the world you're watching from and what time it is there now. Now, prepare yourself for a journey to uncover if humans could ever leave the solar system. Since the earliest times, humans have been fascinated by the night sky. Long before telescopes or rockets, long before modern science could explain the motion of planets or the birth of stars, people stared into the darkness and filled it with meaning. Ancient civilizations told stories about constellations, shaping the stars into heroes, monsters, gods, and animals. To the Greeks, Orion was a mighty hunter forever chasing his quarry across the heavens. To the Egyptians, the belt of Orion aligned with the pyramids, marking sacred connections between earth and sky. The Chinese, the Mayans, the Babylonians, and countless others studied the stars with deep devotion, using them as calendars to track seasons, as maps for navigation, and as guides for rituals. The stars were never just distant points of light. They were symbols of order, beauty, and mystery. This connection between humanity and the stars was not just about myth and storytelling. It also awakened curiosity. Even in the ancient world, thinkers began to wonder whether the stars were distant suns, whether other worlds might circle them, and whether life could exist beyond Earth. The philosopher Epicurus, living more than 2,000 years ago, suggested that the universe must hold countless other worlds, some like ours, some utterly different. To him and to others, the idea that Earth could be unique seemed impossible. This spark of thought that we're not alone and that the universe is wider than our small planet has never gone out. Part of humanity's longing for the stars comes from this curiosity. We are creatures who want to know, to learn, and to understand. When we see something distant, we do not rest until we try to reach it. It is the same spirit that led our ancestors to cross oceans, to climb mountains, and to explore deserts. For them, the horizon was never the end. It was a challenge, a promise of discovery. When early humans first left Africa tens of thousands of years ago, they did not know what they would find, but they kept moving, spreading across continents, guided by an instinct to see what lies beyond. That same instinct now looks upward, not to another continent, but to other worlds. The sea is no longer enough, the mountains are no longer enough, even Earth itself is no longer enough. Our curiosity demands more. But it is not only curiosity that drives us. There is also a deep sense of wonder and awe. When people gaze at the night sky, they often feel small, almost insignificant, standing under the endless expanse of the cosmos. Yet at the same time, they feel connected to something vast and eternal. The stars remind us of how short our lives are, yet they also invite us to be part of something greater. This paradox, feeling small yet dreaming big, is at the heart of our longing. We may be tiny creatures on a fragile world, but our minds can travel farther than light. Our imaginations leap from star to star, building bridges across space before our hands ever can. The longing for the stars also carries with it a desire for survival. Human beings know that life on Earth is fragile. We know that disasters have struck before and could strike again. 65 million years ago, a great asteroid wiped out the dinosaurs, creatures that had ruled the Earth for over 150 million years. If such a thing could happen to them, it could happen to us. Volcanic eruptions, climate shifts, or even our own mistakes could one day threaten human civilization. For many thinkers and scientists, reaching the stars is not just a dream of wonder, it is a necessity. By spreading to other worlds, humanity can ensure its survival, creating a safeguard against extinction. The longing for the stars, then, is partly a longing for security, for a future where our species will continue even if Earth faces catastrophe. Alongside survival, there is also the urge for freedom and adventure. Humans thrive on challenge, on testing themselves against the unknown. From explorers who sailed uncharted seas to mountaineers who braved icy peaks, history shows us that people are willing to risk everything to reach new frontiers. Space is the ultimate frontier, the greatest adventure we can imagine. It is a place of danger and hardship, but also of triumph and discovery. Many dream of standing on another world, of seeing alien landscapes with their own eyes, of experiencing a life unbound by the limits of Earth. For some, this longing is like a fire inside, a restless energy that can only be satisfied by reaching beyond the familiar. Our longing for the stars has grown even stronger in modern times, as science and technology have brought the dream closer. 4 centuries ago, Galileo first pointed his telescope at the heavens and saw moons circling Jupiter, proving that Earth was not the centre of all things. Since then, each new discovery has expanded our view. We now know that our Sun is just one of hundreds of billions of stars in our galaxy, and our galaxy is just one of trillions in the universe. We know that planets are common, and many of them may be like Earth. Telescopes in space, such as the Hubble and the James Webb, have shown us galaxies billions of light years away, glowing like jewels scattered across the dark. Each discovery makes the stars seem both more reachable and more mysterious, fueling our desire to go further. The 20th century turned longing into action. In 1961, Yuri Gagarin became the first human to orbit Earth, circling the planet in a small spacecraft and proving that people could survive beyond the atmosphere. 8 years later, in 1969, Neil Armstrong and Buzz Aldrin walked on the Moon, leaving footprints on a world beyond Earth for the very first time. These moments were not just scientific achievements, they were human milestones. They showed that the dream of reaching the stars was not only poetic but possible. Though the Moon is close compared to the stars, it was a first step, a symbol of what could one day be. Millions around the world watched those events and felt their hearts lift with the same thought. If we can reach the Moon, one day we may reach the planets and beyond. Yet the stars are not only about science or survival, they also touch something emotional, even spiritual. The night sky has inspired religions, philosophies and art for thousands of years. It awakens questions about who we are, why we exist, and what lies beyond death. Many feel that reaching the stars is part of our destiny, a way to fulfill a purpose greater than ourselves. Others see it as a way of connecting with the universe, of becoming part of a story larger than Earth alone. Whether or not one believes in fate, it is hard to deny that the stars call to us in a way that is deeply human. When we speak of travelling beyond our home, we're not just talking about rockets and space stations. We're talking about carrying with us the essence of humanity, our cultures, our stories, our languages, our dreams. If one day we build settlements on Mars or sail to the moons of Jupiter and Saturn, we will bring not only science and technology, but also art, music and laughter. We will bring the full richness of human life. This too is part of our longing, to spread life where there is none, to bring warmth and meaning into the cold emptiness of space. To some, this is a sacred mission, the continuation of life's journey that began billions of years ago in the oceans of Earth. The longing for the stars also has a personal side. Children look up at the sky and dream of becoming astronauts. Writers craft stories of distant galaxies and alien civilizations. Filmmakers bring visions of space travel to life on the screen. Even people who may never leave Earth themselves feel inspired by the idea that humanity as a whole could one day travel among the stars. It is a dream that belongs not just to scientists or explorers, but to everyone. It gives hope, it sparks creativity, and it reminds us that no matter how difficult life may be, there is always something greater to reach for. Of course, the path to the stars is not easy. The distances are immense, the dangers many, and the costs high. Travelling to even the nearest star would take tens of thousands of years with current technology. Yet these challenges do not diminish the longing, they make it stronger. Just as early explorers crossed dangerous seas without knowing what lay ahead, so too will future generations find ways to cross the oceans of space. The dream does not fade because it is difficult, it endures precisely because it is difficult. Humanity has always risen to meet great challenges, and space is simply the greatest of them all. From space, astronauts describe something called the overview effect, a shift in consciousness that comes from seeing Earth as a small, fragile and beautiful blue sphere floating in the dark. From that height, national borders disappear, conflicts seem trivial, and the planet feels united and precious. In reaching for the stars, we also learn more about ourselves and our home. We realise how rare and valuable life is, and how important it is to protect it. The longing for the stars, then, is not about abandoning Earth, but about cherishing it even more. By stepping into the wider universe, we gain wisdom about the place we began. The solar system is an astonishingly vast and intricate collection of celestial bodies, each moving through space with a rhythm set by the laws of gravity. Its sheer size is difficult for the human mind to truly grasp. Even the nearest planets feel separated by enormous distances, far beyond everyday experience. If one were to imagine travelling from the Earth to the Sun, the journey would cover about 150 million kilometres, a distance astronomers call 1 astronomical unit. This is already a staggering stretch, yet it is just the beginning of the immense reaches of the solar system. Every planet in our cosmic neighbourhood orbits the Sun at its own pace, following paths determined by their masses and the Sun's gravitational pull. Mercury, the closest planet, circles the Sun in just 88 Earth days, while Venus takes about 225 Earth days to complete one orbit. Earth, our home, revolves around the Sun in 365 days, giving rise to the familiar calendar year. Mars, farther away, takes nearly 687 Earth days for a single orbit. The outer planets such as Jupiter, Saturn, Uranus and Neptune require increasingly longer times, with Neptune needing about 60 Earth years to make a single revolution. These periods illustrate just a fraction of the immense spatial and temporal scales involved in our solar system. Distances within the solar system expand dramatically as one moves outward. Jupiter, the largest planet, is roughly 778 million kilometres from the Sun, a figure more than 5 times the distance from Earth. Saturn follows at about 1,433 million kilometres, Uranus at nearly 2,870 million kilometres, and Neptune, the outermost recognised planet, at approximately 4,500 billion kilometres. Beyond Neptune lies the Kuiper Belt, a vast region of icy bodies and dwarf planets, extending to nearly 10 billion kilometres from the Sun. These figures, when expressed in kilometres, can feel abstract, yet they provide a glimpse into the enormous expanses of space that planets, moons, asteroids, and comets traverse. The size of the planets themselves contrasts sharply with the vast distances separating them. Earth has a diameter of roughly 12,740 kilometres, while Jupiter, the gas giant, spans nearly 140,000 kilometres, making it over 10 times wider than Earth. Saturn's diameter is about 120,000 kilometres, Uranus measures roughly 51,000 kilometres, and Neptune is close to 49,000 kilometres across. When compared to the spaces between them, even the largest planets appear as tiny specks, moving through a nearly empty expanse that stretches for billions of kilometres. Moons orbit their planets at distances that can rival the distances between planets themselves. Earth's moon, for instance, is nearly 400,000 kilometres away, roughly 30 times the Earth's diameter. Jupiter's largest moon, Ganymede, orbits at nearly 1,080,000 kilometres, while Saturn's Titan circles at over 1,200,000 kilometres from its planet. These orbital distances further underscore the scale and complexity of the solar system, where celestial bodies interact with one another across vast cosmic voids. Even the Sun, which dominates the solar system with its immense gravity, is relatively small compared to the distances it governs. Its diameter is about 1,392,000 kilometres, a figure that dwarfs Earth, yet the solar system stretches for billions of kilometres beyond it. The Sun's gravity reaches far into space, keeping planets, asteroids, and comets bound in their paths, and even extending influence to the distant Oort cloud, where icy objects may orbit at distances exceeding 100,000 astronomical units. The interplay between such a massive star and its far-flung companions demonstrates the delicate balance and precise mechanics governing the solar system's structure. The asteroid belt situated between Mars and Jupiter presents another fascinating dimension of scale. Its objects range from tiny grains of rock to dwarf planets like Ceres, which is nearly 940 kilometres across. The belt spans a distance of about 300 million kilometres, a vast gap peppered with countless fragments of rock and metal. remnants from the early formation of the solar system. These bodies travel at tremendous speeds, often tens of kilometers per second, illustrating both the energy and vastness present even within what might seem like a small region of space. Comets provide yet another lens into the solar system's enormity. These icy wanderers often originate in the distant reaches of the Kuiper Belt or the Oort cloud, where their orbits can stretch for thousands, sometimes millions of kilometers. When they approach the Sun, their velocities increase dramatically, tracing elongated paths that can take decades, centuries, or even millennia to complete a single journey. The trajectory of Halley's Comet, for example, takes it approximately 76 years to orbit the Sun, moving from the outer limits of the solar system to its inner regions and back again. These journeys highlight the vast scales not just in distance, but also in time, that define celestial motion. Light itself, moving at a speed of nearly 300,000 kilometers per second, still requires significant time to traverse the solar system. Sunlight takes about 8 minutes and 20 seconds to reach Earth. To reach Jupiter, it requires roughly 43 minutes and about 5 hours to arrive at Neptune. The notion that light, the fastest thing in the universe, takes hours to cover the distance to the outer planets offers a striking perspective on the immensity of space. Even travelling at speeds far beyond human capability, the distances between objects in the solar system demand years of transit. Exploring the edges of the solar system has revealed even greater expanses than previously imagined. The Voyager spacecraft, launched in 1977, took decades to reach the outer planets, eventually entering interstellar space more than 40 years later. Their journey, now extending beyond 20 billion kilometers from Earth, illustrates the monumental distances required to leave the gravitational influence of the Sun. Despite travelling at tens of thousands of kilometers per hour, these probes only now are crossing the frontier of the solar system, emphasizing the staggering scales involved. The solar system also contains vast regions of seemingly empty space, yet these voids are crucial to understanding its full magnitude. Between planets, moons, and belts of asteroids lie immense stretches of space, largely devoid of matter. These regions, although empty by human standards, provide the stage on which gravitational forces act, allowing planets to maintain their orbits and comets to follow their elongated paths. The emptiness itself becomes a measure of the system's size, highlighting distances that are almost incomprehensible compared to everyday life. Objects beyond Neptune, known as trans-Neptunian objects, reveal the outer reaches of the solar system. These bodies, including dwarf planets like Eris and Haumea, occupy regions hundreds of times farther from the Sun than Earth. Their orbits can take thousands of years to complete, moving through the cold, dark expanses of space where sunlight is faint and temperatures approach absolute zero. These remote bodies expand our understanding of the solar system, illustrating that its boundaries are not defined by visible planets alone, but stretch into distant, almost alien realms. Gravity binds the solar system together, yet its influence weakens with distance. The Sun's pull, although dominating nearby planets, becomes faint in the farthest reaches, allowing for loosely bound objects in the Oort cloud to drift far from its centre. This delicate balance of forces demonstrates the incredible scale, where even the strongest gravitational influence fades over billions of kilometers, showing how tenuous connections can still govern the motion of countless objects. The solar system's formation, billions of years ago, set the stage for the vast distances observed today. Gas and dust coalesced under gravity, forming the Sun at the center and allowing planets to take shape in orbits that would persist for eons. Collisions, accretion, and the gradual migration of planets contributed to the spacing observed, creating gaps, belts, and far-flung bodies in stable paths. The history of the solar system, therefore, is embedded in its scale, with every distance, orbit, and region, reflecting the processes that shaped it over 4.5 billion years ago. Our understanding of the solar system continues to evolve as telescopes, spacecraft, and computational models probe these vast distances. Observations reveal details of planetary atmospheres, ring systems, and surface features, yet even with advanced technology, the immensity of space challenges comprehension. For instance, light from the outermost known dwarf planet Sedna takes over 20 hours to reach Earth, reminding us that even with the speed of light, The solar system is enormous beyond ordinary human experience. The scale of the solar system also affects exploration and travel. Sending spacecraft to even the nearest planets requires years of planning, immense energy, and precise calculations. Missions to Mars take about 6 to 9 months, while reaching Jupiter can require over 6 years. The farther one aims, the greater the challenge, as distances increase exponentially. A journey to Neptune, for instance, would take more than a dozen years with current technology, illustrating that our perception of nearby is vastly different on a cosmic scale. Comprehending the solar system's vastness also enriches our appreciation of the Sun's role. Despite being one among billions of stars in the galaxy, it provides the gravitational anchor and energy source essential for life on Earth and the orbits of planets. Its influence stretches billions of kilometers, guiding every orbit and motion, shaping the environment of the entire system. The interaction between the Sun and planets creates seasons, climates, and dynamic processes on worlds near and far, showing that even in immense space, the central star remains pivotal. Distances within the solar system are not only vast but also dynamic. Planetary orbits are not perfect circles but ellipses, meaning distances vary across the year. Earth's closest approach to the Sun, called perihelion, occurs in early January about 147 million kilometers away, while its farthest distance, or aphelion, occurs in early July, at roughly 152 million kilometers. Similar variations exist for other planets, making the solar system not only immense but constantly shifting, with each body tracing a unique, elliptical path through space. The interplay between size and distance also affects phenomena such as eclipses, transits, and planetary alignments. From Earth, the Sun appears nearly 500 times larger than the Moon, yet it is about 400 times farther away, creating precise conditions for solar eclipses. These interactions, observable from our tiny vantage point, underscore the harmony and scale of celestial mechanics, revealing that vast distances do not preclude moments of striking alignment and beauty. Even within the solar system, the notion of scale extends to time. Planetary rotations, orbital periods, and long-term gravitational interactions occur over intervals that dwarf human lifespans. Jupiter, completing a rotation in just under 10 Earth hours, contrasts with Neptune's rotation of over 16 hours. Long-term changes in orbit due to gravitational interactions among planets unfold over millions of years, illustrating that the solar system's vastness encompasses not only space, but the deep time over which motions unfold. Meteoroids, comets, and asteroids highlight the ongoing dynamism within the solar system. Their high velocities and vast orbits create opportunities for collisions, occasional impacts on planets, and shifting paths that reveal the system's energetic nature. The Chelyabinsk meteor, which entered Earth's atmosphere in 2013, travelling at about 19 kilometers per second, offered a small but vivid reminder that even tiny bodies traverse enormous distances at tremendous speeds, interacting with planets across billions of kilometers of space. The vastness of the solar system challenges the human imagination. Even the notion of travelling from one planet to another requires rethinking scale, time, and distance. The physical distances demand fuel, energy, and precision navigation, while the timescales necessitate long-term planning and endurance. This immensity inspires scientific inquiry, pushing engineers, astronomers, and explorers to innovate technologies capable of traversing regions once thought unreachable, turning abstract distances into achievable journeys. Understanding the solar system also enhances our appreciation of Earth's uniqueness. Among the planets, Earth harbours life, water, and a dynamic atmosphere shaped by its distance from the Sun and its interactions with the Moon. The scale of the solar system frames Earth's position as a relatively tiny world in a vast cosmic arena, emphasizing both its fragility and its extraordinary capacity to sustain life in a system dominated by extremes of distance, temperature, and radiation. Even the outer limits, such as the Oort cloud, extend the concept of the solar system into near interstellar space. Objects in this distant reservoir of icy bodies may travel tens of thousands of astronomical units from the Sun, slowly orbiting over millions of years. These remote regions, largely unexplored, define the outer boundaries of solar influence and demonstrate the staggering scale where the sun's reach extends almost invisibly into the darkness beyond the planets. Human exploration, from telescopes to spacecraft, continues to reveal the solar system's intricacies. Missions like New Horizons, which flew past Pluto in 2015 after a 9-year journey, provide data on distant worlds, revealing mountains, ice plains, and atmospheric processes. Such achievements highlight both the enormous distances traversed and the challenges of operating in regions where sunlight is weak, temperatures are extreme, and communication delays stretch over hours. Every new observation reinforces the vastness and diversity of the solar system, showing that each planet, moon, and small body occupies a unique place in the immense cosmic arena. The solar system's scale also affects potential future human exploration. Travelling beyond Mars or establishing outposts on moons such as Europa or Titan would require understanding distances measured in millions or billions of kilometres, planning for years-long missions and ensuring life support and propulsion systems capable of operating over immense stretches of space. The concept of local in the solar system differs radically from earthly standards, where distances and durations are compressed. In space, the scale challenges not only engineering but human perception and endurance. Every exploration mission deepens our understanding of gravitational influence, orbital dynamics, and the scale of space. Even robotic missions to the Moon, which is only about 400,000 kilometers away, provide insight into how humans might navigate larger distances. Understanding the Moon's gravitational effect, orbital period, and interaction with Earth prepares scientists and engineers for journeys to Mars, Jupiter's moons, or even the outer planets, where the distances multiply by orders of magnitude. Astrophysical observations from Earth and orbiting telescopes complement direct exploration, offering measurements of distances, planetary sizes, and orbital velocities. Techniques such as radar ranging, parallax measurements, and spacecraft telemetry provide precise data, converting abstract figures into comprehensible numbers. By quantifying distances in astronomical units, light minutes, and kilometers, scientists transform the immensity of the solar system into a framework that, while vast, can be analysed, understood, and navigated. The solar system's vastness also fosters philosophical reflection. Humans, confined to one small planet, must consider their place in a system that spans billions of kilometers, where even the largest planets appear small against the emptiness of space. This perspective shapes scientific curiosity, inspiring generations to look outward, to study orbits, gravitational interactions, and distant worlds, and to ponder how life might survive or thrive across such enormous distances. Even seemingly empty regions such as interplanetary space between Jupiter and Saturn, or beyond Neptune, are filled with faint dust, charged particles, and cosmic radiation. Understanding these subtleties requires precise measurement and awareness of the vast distances over which effects accumulate. Cosmic rays, for instance, travel from distant stars, interacting with the solar wind and magnetic fields, illustrating that even in emptiness, vast spaces contain dynamics and influences that shape the solar system. The immensity of the solar system is further revealed by the scale of its minor bodies. Dwarf planets, asteroids, and comets range from mere kilometers across to over 2,000 kilometers in diameter. Each follows paths governed by gravity, moving at tremendous velocities across millions of kilometers. The collective motion of these small bodies creates belts, clouds, and rings that structure the system, adding complexity to an already vast expanse, showing that even minor objects contribute to the grandeur and scale of the solar system. Through centuries of observation, human understanding of the solar system's scale has grown from simple models to complex three-dimensional maps. Early astronomers estimated distances and sizes with limited tools, imagining planets as points of light. Yet today, advanced instruments allow precise measurement of planetary diameters, orbital velocities, and positions billions of kilometers away. The evolution of knowledge itself reflects the challenge of comprehending such vast distances, emphasizing that understanding the solar system is an ongoing process that stretches human curiosity as far as space itself. Even from a mathematical perspective, the distances and scales involved are staggering. Calculating orbital periods, velocities, and trajectories requires understanding that the numbers involved span millions, billions, and even trillions of kilometers. The interplay between mass, distance, and gravitational force creates a system of precise balance, where even small deviations could result in massive changes over astronomical timescales. This mathematical framework helps turn the incomprehensible distances into predictable, navigable space, demonstrating that vastness does not preclude order or understanding. The stars that light up the night sky may seem close, twinkling just above us, yet in truth, they are astonishingly far away. When we look at even the nearest star, apart from our Sun, we are peering across distances that are almost impossible to truly imagine. The closest star system to our Sun is called Alpha Centauri, which lies a staggering 4.37 light-years away. To put this into numbers, we can feel a little more. 1 light-year, the distance that light travels in a single year, is roughly 9,400,000,000,000 kilometers. This means that the light from Alpha Centauri, travelling at nearly 300,000 kilometers per second, still takes over 4 years to reach us. Our minds struggle with such distances because we live in a world measured in kilometers or miles, where we travel hundreds or even thousands of kilometers in a day, not trillions. Thinking about the nearest stars as mere points of light is like trying to imagine mountains in the middle of a vast ocean. They exist on a scale far beyond ordinary human experience. The distances become even more mind-boggling when we consider other stars beyond Alpha Centauri. Proxima Centauri, the smallest and closest of the 3 stars in the Alpha Centauri system, is slightly closer at 4.22 light-years away. Even so, that is still over 40 trillion kilometers. If a modern spaceship like Voyager 1, which travels at roughly 17 kilometers per second, was sent to Proxima Centauri, it would take more than 70,000 years to get there. 70,000 years is longer than all recorded human history, longer than the rise and fall of countless civilizations. Our ancestors, who first drew in caves and built the pyramids of Egypt, would be the great-great-great-grandparents of travellers that might finally reach that distant star. This makes one realise how astronomical distances are not just large, they are almost beyond human comprehension. Stars beyond Alpha Centauri are even more distant, and as we peer further into the Milky Way, the numbers grow exponentially. The closest bright star after Alpha Centauri is Barnard's star, which lies roughly 6 light-years away, a journey that would take more than 100,000 years with our fastest current spacecraft. Even within our own galaxy, which is just one of billions in the universe, stars are separated by vast, seemingly empty voids. Our galaxy, the Milky Way, stretches over 100,000 light-years across, and yet most of that immense distance is not filled with stars. Instead, space is largely empty, a dark ocean in which the stars float like distant lighthouses. Travelling from one star to another is not like hopping from city to city. It is more akin to crossing the entire continent of Asia by walking, then realising that continents are filled with oceans far larger than anything we have ever crossed on Earth. Understanding the scale of space also helps us realise why interstellar travel is such a daunting challenge. When we speak of travelling to even the nearest stars, we're talking about journeys that span times longer than human lifetimes. Unlike the Moon, which is just over 300,000 kilometres away, or Mars, which at its closest comes to roughly 55 million kilometres, nearby stars are many millions of times farther away. Even with theoretical spacecraft travelling at 10% of the speed of light, a speed unimaginably fast compared to anything humans have achieved, the journey to Alpha Centauri would still take over 40 years. That is a lifetime, an entire human career spent travelling in the void of space. And that assumes we could build engines capable of sustaining such speeds and protect travellers from the deadly radiation that exists between the stars. The sheer distances make clear why humanity has so far only dreamed of leaving our solar system, rather than actually doing it. Light itself, travelling at the universe's ultimate speed limit, reveals the immensity of these distances. The photons of light we see from Proxima Centauri today actually left the star more than 4 years ago. That means the light we enjoy tonight is a window into the past, showing the star as it was long before we looked up. When we consider stars that are tens, hundreds, or even thousands of light-years away, the concept of looking into the past becomes even more dramatic. We are literally seeing ancient light, ancient events, and perhaps even stars that no longer exist in the form we see. In this way, distance is not just a measure of space, it is a measure of time, connecting us to events that occurred long before we existed. The nearest stars are not only distant in space, they are distant in terms of the resources and energy required to reach them. The energy needed to accelerate a spacecraft to even a fraction of the speed of light is enormous, far beyond our current technology. Chemical rockets, the mainstay of human space travel for decades, are utterly insufficient for interstellar journeys. To reach Alpha Centauri in a reasonable human timescale, we would need propulsion systems capable of accelerating a spacecraft to tens of thousands of kilometers per second, maintaining that speed and then decelerating upon arrival. Concepts like nuclear propulsion, light sails, and even theoretical ideas such as antimatter engines have been proposed, but none are yet feasible. The distances of the nearest stars force us to confront the limits of our technology and imagination. Stars are not just distant objects, they are destinations that challenge our very concept of travel. Even sending robotic probes requires decades or centuries of planning. The Voyager spacecraft, launched in 1977, are currently leaving our solar system, travelling at 17 kilometers per second. At that speed, reaching Alpha Centauri would take tens of thousands of years. In comparison, the distance to the Moon travelled by Apollo astronauts in just 3 days seems minuscule. The disparity highlights that while human exploration has pushed the boundaries of the solar system, the stars remain stubbornly out of reach. Each increase in distance multiplies the difficulty, turning what seems like a simple journey into an epic challenge of physics, engineering, and patience. Beyond the engineering challenges, the immense distances of nearby stars also affect how we think about communication and coordination. Signals, including radio waves, travel at the speed of light. Even messages sent to the nearest star would take over 4 years to arrive. This means that any hypothetical colony near Alpha Centauri could not communicate with Earth in real time. A conversation between Earth and such a colony would involve years of waiting for replies, a delay so long that it fundamentally changes how we would live and govern in interstellar space. Time itself becomes a barrier, as significant as distance or energy, reminding us that the nearest stars exist in realms almost untouchable to human experience. Observing these nearby stars also requires special tools and techniques. Telescopes on Earth and in space allow astronomers to measure their positions, movements, and even their potential planets. Proxima Centauri, for instance, hosts at least one known planet, a rocky world in its habitable zone where conditions might allow liquid water. Even though this planet is only a few trillion kilometers away, sending a spacecraft to study it directly would take tens of thousands of years with our current methods. Instead, we rely on indirect observations, detecting wobbles in the star's motion, slight dips in brightness, and other clues to understand these distant worlds. The stars are close enough to study, yet still so far that direct exploration seems almost mythical. The distances to the nearest stars also reveal the scale of our solar system in contrast. The outer edge of the solar system, where the sun's influence dwindles, extends for about 1 light day, an almost unimaginably large distance in its own right. Yet even at this vast scale, the nearest star lies more than 15,000 times farther away than the edge of our solar system. This comparison emphasizes that our sun is not a lonely point in the sky. It is a beacon surrounded by darkness, with other stars isolated in the vast void. The void between stars is filled with mysteries, cosmic dust, magnetic fields, and the thin interstellar medium that carries the faint whispers of distant cosmic events. Humanity has dreamed of reaching the stars for centuries, and those dreams are inspired by the immense challenge these distances present. Ancient astronomers, looking up at the night sky, could not have imagined the numbers involved, yet they understood that the stars were very far away. Today we can calculate distances precisely, measure parallax shifts, and even detect planets orbiting these far-off suns. Knowing that Alpha Centauri is more than 4 light-years away gives context to the scale of our ambitions. Reaching it would require not just technological innovation, but a rethinking of time, energy, and human endurance. The stars are not just points of light, they are monuments to the scale of the universe and the limits of our reach. Travelling to the nearest stars forces us to consider life in entirely different terms. We must think about generations, about spacecraft functioning for centuries without human maintenance, about humans living their entire lives in enclosed artificial environments. The distances are so great that interstellar travel is not simply a matter of speed. It becomes a question of survival, planning, and vision. Even the concept of fuel becomes a problem. Carrying enough to reach another star is nearly impossible with conventional means. We must imagine technologies that harness energy efficiently, perhaps using cosmic forces we have only begun to understand. Each nearby star represents a challenge far greater than anything we have faced, yet each one also represents hope for discovery, adventure, and understanding. Stars like Sirius, located over 8 light-years away, and Epsilon Eridani at 10.5 light-years, are examples of the many neighbours our Sun has in the local cosmic neighbourhood. Though they appear bright to our eyes, their brightness is a trick of distance. They shine with enormous energy, yet that energy has to travel across trillions of kilometres before reaching us. The light we see tonight left Sirius more than 8 years ago, making it a messenger from the past. These stars serve as reminders that the universe operates on scales vastly beyond our daily experience, with distances measured not in hours or days, but in years, decades, and millennia. Considering interstellar travel also forces us to think about speed limits and physics itself. Nothing in the universe can travel faster than light, and that places a hard limit on how quickly we can reach other stars. Even if we could approach light speed, the energy requirements and relativistic effects, time slowing down, mass increasing, become significant challenges. Practical travel at even a fraction of light speed requires rethinking propulsion, energy storage, and life support. In a sense, the nearest stars are not just far away in space, they are far away in possibility, testing the limits of human ingenuity. The distances also affect our understanding of time in profound ways. Travelling to Alpha Centauri at a significant fraction of the speed of light would mean that travellers would experience time differently than people on Earth. The journey might feel shorter for them, yet decades or centuries would pass for those left behind. This introduces a strange disconnect. The nearest stars are close in the eyes of the traveller but almost impossibly distant to everyone else. Time and distance intertwine, emphasizing that interstellar travel is not just a technological challenge, but a philosophical and human one. Astronomers continue to search for planets around nearby stars, hoping to find worlds that might host life or be suitable for future human exploration. Proxima b, orbiting Proxima Centauri, has captured the imagination of scientists and the public alike. Yet sending a probe to study it directly remains a monumental challenge. Even sending robotic explorers using the fastest conceivable propulsion systems would take decades to arrive, emphasizing that the nearest stars are both tantalizingly close in cosmic terms and overwhelmingly distant in human terms. Every discovery brings hope, but also underscores the vastness of the void we must cross. In essence, the nearest stars teach us humility. They remind us of our smallness in a universe of incomprehensible scale. They highlight the limits of our technology, the patience required for true exploration, and the courage needed to even dream of such journeys. Travelling to these stars is not a near-term goal. It is a challenge that stretches the imagination, demands patience, and inspires generations. Each flicker of starlight is a silent invitation, a distant beacon calling us to think beyond our solar system, to consider what it means to explore, endure, and reach across the almost infinite dark. The challenge of distance shapes our exploration strategy today. Robotic missions, like those we send to the outer planets, become the first steps toward understanding how to survive and operate in deep space. Observations from telescopes, both on Earth and in orbit, allow us to study stars light-years away without leaving our planet. Techniques like spectroscopy, astrometry, and direct imaging reveal the nature of these stars and their planets, providing the knowledge that will one day make human travel feasible. Each discovery is a small victory against the vastness, a step closer to bridging the unthinkable distances that separate us from our nearest neighbours in the galaxy. Even with all the obstacles, humanity continues to gaze at the stars with longing. The nearest stars are not just physical objects, they are symbols of ambition, curiosity, and the human desire to explore. Knowing their distances forces us to plan carefully, dream boldly, and innovate constantly. While Alpha Centauri, Proxima Centauri, and other nearby stars may seem unreachable now, understanding their scale prepares us for the challenges of the future. Every calculation, every telescope image, every theoretical propulsion concept brings us a little closer to the dream of interstellar travel, transforming what seems like an impossible journey into a long-term goal that might one day be realized. In conclusion, the nearest stars are both near and far, close enough to be observed in detail, yet distant enough to test the limits of human endurance, technology, and imagination. They are measured in light years, trillions of kilometers, and decades of travel at the fastest speeds humanity can achieve. Each star is a reminder of the vast emptiness that separates worlds, the difficulty of interstellar travel, and the need for ingenuity, patience, and determination. Understanding these distances transforms our perspective, showing us that the universe is a realm of immense scale, mysterious beauty, and extraordinary challenge, and that the nearest stars are our first test, our first opportunity, and our first dream beyond the safety of our solar system. The night sky, filled with points of light, is a map of challenges and possibilities. Each star invites contemplation, study, and imagination. They demand respect for the scales of the cosmos while inspiring the hope that one day, through generations of effort, courage, and discovery, humans might reach across the void. The nearest stars are not merely distant suns. They are beacons of curiosity, endurance, and the timeless desire to venture farther than we have ever gone before. They remind us that the universe is enormous, that distances are staggering, and that the dream of touching another star is the ultimate testament to human aspiration. The scale of space, revealed by the distance to even the nearest stars, transforms the way we view our place in the universe. From Alpha Centauri to Barnard's star, from Sirius to Epsilon Eridani, each star represents a frontier, a possibility, and a challenge. They are far beyond the reach of current human travel, yet close enough to be understood through observation and theory. They provide context for our ambitions, a measure of the vastness that separates Earth from other worlds, and a reminder that every journey into the stars, whether by mind, telescope, or eventually by spacecraft, begins with understanding the incredible distances that separate us from these celestial neighbours. If humans ever hope to leave the solar system, the nearest stars will be the first destinations, and the distances we have considered show why such travel is an extraordinary challenge. Light years, trillions of kilometres, decades or even centuries of travel, technological limitations, energy requirements, and human endurance all combine to make interstellar journeys a monumental endeavour. Yet the stars continue to shine, patiently waiting, offering both inspiration and perspective. They remind us that exploration is a slow, difficult, and often multi-generational process, and that even the closest stars are worlds apart in terms of what must be achieved to reach them. The nearest stars shining silently across the dark expanse are not just objects in the sky. They are milestones of ambition, knowledge, and the human desire to journey beyond the familiar. They reveal the limits of our current technology, the vastness of cosmic distances, and the immense challenge of leaving our solar system. They are invitations to think beyond the present, to plan across generations, and to dream in scales far beyond a human lifetime. Reaching them will require everything humanity can muster: courage, patience, creativity, and perseverance. Until that day comes, they remain distant lights, guiding our curiosity and imagination toward the stars. The journey to the nearest stars is not a story of quick success, but of long-term vision. From the 4.37 light-years to Alpha Centauri, to the 8 or 10 light-years to other nearby suns, each distance is a barrier and a goal. Humans must develop new technologies, new ways of sustaining life, and new methods of travelling through the void if we are ever to turn these distances from abstract numbers into real journeys. The nearest stars remind us of our limitations, yet they also define the scale of our ambitions and the depth of our dreams. They are both far and near, impossible yet inevitable in the imagination of those who yearn to explore. Even in the modern era, the nearest stars continue to challenge and inspire. Astronomers measure their movements, scientists calculate the energy needed to reach them, and dreamers envision missions that span decades or centuries. They are beacons of possibility, inviting thought about what it means to leave home, cross unimaginable distances, and confront the void. The distances to these stars define the boundary between our solar system and the galaxy, between what is currently possible and what may one day be achievable. They are both a measure of reality and a spark for imagination, demanding respect for scale and inspiring hope for the future. The knowledge of the nearest stars and their distances is fundamental to understanding the universe and our place within it. It shows us that even our most ambitious dreams are small in the grand scale, yet still meaningful. Alpha Centauri, Proxima Centauri, Barnard's Star, Sirius, and Epsilon Eridani are not just points of light. They are distant suns that challenge our understanding of space, time, and human potential. Their vast separations illustrate the limits of current technology, the requirements for interstellar travel, and the scale of ambition needed to reach beyond our solar system. Each star is a reminder that the universe is vast, life is fragile, and human curiosity is boundless. The nearest stars, while light years away, are the first steps toward humanity's broader exploration of the galaxy. They represent challenges to our technology, tests of endurance, and goals for future generations. They force us to think beyond lifetimes, to consider civilizations that can plan, work, and dream over centuries. The vast distances between these stars remind us that space is not an empty void, but a domain that requires understanding, effort, and imagination. They are the ultimate destinations, whose distances are both humble and inspiring, urging humanity to look beyond its home and contemplate a journey that might one day extend across the stars themselves. The night sky, full of stars like Alpha Centauri and Proxima Centauri, tells a story of distance, challenge, and possibility. Their light travels across unimaginable distances to reach us, and their separation from Earth defines the enormity of space. Understanding how far the nearest stars truly are transforms the way we think about travel, ambition, and the universe itself. These stars are the first markers of the interstellar frontier, setting the scale for all future exploration. The idea of travelling to the stars has fascinated humanity for centuries, long before we even had the technology to leave our own planet. Long ago, people looked up at the night sky, mesmerised by the countless pinpricks of light scattered across the darkness, and wondered what it would be like to reach those distant points of brilliance. Stories and myths filled with cosmic journeys and celestial voyages were common in many ancient cultures, yet they remained purely imaginative, the realm of dreams rather than practical plans. Humans have always been captivated by the unknown, and the stars represented the ultimate unknown, a vast ocean of possibilities that no ship at the time could ever hope to sail. As centuries passed, these imaginative tales slowly evolved into what we now call science fiction, which began to turn dreams into stories that sometimes hinted at real science. In the early 19th century, literature started to explore journeys beyond the Earth in more structured ways. Writers such as Jules Verne and H.G. Wells began to describe interplanetary travel using the tools of science known in their day, though still largely speculative. Jules Verne, in works such as From the Earth to the Moon, written in 1865, imagined a massive cannon shooting a projectile containing human passengers toward the moon. While the physics of such an endeavour were impossible by modern understanding, Verne's ideas were remarkable in that they attempted to merge imagination with scientific reasoning, using the knowledge of the time to inspire wonder. H.G. Wells, in his 1898 classic The War of the Worlds, explored not human journeys to other worlds, but the idea that beings from distant planets could travel to Earth. In doing so, he turned the imagination outward, portraying the stars as not merely destinations but as homes to other life and civilization, further fueling humanity's curiosity about space. These literary works planted the seeds for more serious thought about interstellar journeys, showing that ideas of travelling to the stars could be discussed in a semi-scientific way, even if the technology was not yet anywhere near capable. By the early 20th century, scientific understanding had advanced considerably. Concepts of rocketry, physics, and space began to mature, and a few visionary thinkers started to move the notion of interstellar travel from fiction toward plausible scientific proposals. One of the most influential figures in this movement was Konstantin Tsiolkovsky, a Russian scientist and engineer born in 1857. Tsiolkovsky is often called the father of astronautics because he was among the first to mathematically describe the principles that would make space travel possible. In 1903, he published his now famous work, The Exploration of Cosmic Space by Means of Reaction Devices, in which he introduced the rocket equation, a mathematical formula showing how rockets could escape the pull of Earth's gravity. While Tsiolkovsky focused mainly on reaching Earth orbit and other planets within our solar system, his ideas laid the groundwork for the possibility of travelling beyond the solar system one day. He speculated about spacecraft that could be powered by solar sails, a concept still explored today, and imagined multi-generational ships that could carry humans across vast distances to other stars, even if such journeys would take centuries. His work transformed space travel from a dream into something that could, at least in principle, be engineered. Around the same time, in Germany, another visionary, Hermann Oberth, was developing similar ideas. Born in 1894, Oberth published The Rocket into Interplanetary Space in 1923, which outlined not only the principles of rocketry, but also the potential for humans to explore planets and, by extension, stars. Oberth speculated on using nuclear energy for propulsion, understanding that conventional chemical rockets might never suffice for the distances required to reach other star systems. His work, along with Tsiolkovsky's, inspired a generation of engineers and scientists, many of whom would later contribute to the early space programs in the mid-20th century. The interwar period, particularly in Europe, became a time of rapid imagination and theorizing about the possibilities of leaving Earth, and these scientific proposals were informed by both rigorous mathematics and the imaginative spark of science fiction. The United States also contributed to early scientific speculation about interstellar travel. In the 1930s and 1940s, scientists like Robert Goddard began experimenting with liquid-fueled rockets, which were far more powerful than earlier solid-fuel designs. Goddard, born in 1882, dreamed of sending rockets to the Moon, and even to the planets, laying the practical groundwork for space exploration. Though Goddard's focus was initially within the solar system, his experiments demonstrated that controlled propulsion and navigation through space were possible, providing the first steps toward any future interstellar mission. His work received mixed reactions at the time, with some newspapers mocking his ideas as fanciful, but it eventually became the foundation for the space age. After the Second World War, interest in interstellar travel grew alongside advances in rocketry and nuclear physics. The wartime development of long-range missiles, including the German V-2 rocket, provided engineers with concrete demonstrations of controlled propulsion over vast distances. Scientists who had worked on these projects, including Werner von Braun, began considering how the same principles could be applied to space exploration. By the 1950s, proposals for interstellar travel were appearing in scientific journals, often based on ideas of nuclear propulsion or highly efficient engines capable of approaching the speed of light. Concepts such as the Bussard ramjet, proposed by physicist Robert W. Bussard in 1960, imagined spacecraft that could scoop interstellar hydrogen to fuel a nuclear fusion engine, allowing them to travel far beyond the solar system without carrying an impossible amount of fuel. These ideas were ambitious, bordering on the edge of technological plausibility, yet they were grounded in scientific reasoning rather than purely imaginative storytelling. During the same period, the rise of science fiction in popular culture helped inspire both public interest and scientific thinking about interstellar journeys. Authors such as Isaac Asimov, Arthur C. Clarke, and Poul Anderson wrote stories that included long-distance space travel, generation ships, and encounters with alien civilizations. Clarke, born in 1916, famously proposed the use of geostationary satellites for communication in 1945, demonstrating his talent for predicting future technology. In his fiction, he often explored how humanity might one day reach other stars, blending meticulous scientific reasoning with compelling narrative. Science fiction became more than entertainment. It became a laboratory for ideas, where writers and readers alike could explore the consequences of human journeys across light years. The interplay between imagination and scientific speculation during this period helped establish interstellar travel as a serious topic of discussion rather than a mere fantasy. By the 1960s, scientists began to develop more detailed and quantitative studies of interstellar travel. Projects such as Project Orion, initiated in 1958, explored the feasibility of nuclear pulse propulsion, where controlled nuclear explosions could propel a spacecraft at extraordinary speeds. The concept was startlingly bold. A spacecraft could, in theory, be accelerated to a significant fraction of the speed of light, making travel to nearby stars, though still taking decades or centuries, potentially feasible. Concurrently, theoretical studies of the limitations imposed by relativity and energy requirements helped refine ideas about what was truly possible. It became clear that interstellar travel would demand technologies far beyond conventional rockets, possibly including antimatter engines or light sails driven by powerful lasers, concepts that scientists were only beginning to explore in theory. These studies marked a shift from purely imaginative proposals to serious physics-based planning, even if practical implementation remained decades away. The period also saw the beginning of thought experiments about the social and ethical implications of interstellar journeys. Multi-generational ships, for instance, would require self-sustaining communities capable of surviving for centuries without contact with Earth. Writers and scientists speculated on the psychological, sociological, and biological challenges of such voyages, including how humans might adapt to closed ecosystems and limited resources over multiple generations. These considerations highlighted that interstellar travel was not just an engineering problem, but a profoundly human one, involving culture, ethics, and survival. Early proposals began to take a holistic view, recognizing that the obstacles to reaching the stars were as much social as technological. In the 1970s and 1980s, space agencies began exploring the potential for interstellar probes, even if crewed missions remained distant dreams. The Voyager spacecraft, launched in 1977, were designed to leave the solar system, eventually entering interstellar space. While they would not reach another star for tens of thousands of years, the idea of sending objects beyond our solar neighborhood captured the imagination of scientists and the public alike. These missions demonstrated that humanity could at least begin to bridge the gap between our solar system and the wider galaxy, providing valuable data on the interstellar environment and the challenges of long-duration space travel. Even robotic missions became part of the broader narrative of interstellar exploration, proving that reaching beyond our immediate celestial neighborhood was not purely theoretical. The evolution from science fiction to scientific proposal continued as new technologies and theoretical insights emerged. Laser propulsion, solar sails, and fusion engines became recurring topics in academic literature, while thinkers such as Freeman Dyson and Carl Sagan speculated on the long-term possibilities of reaching other stars. Dyson, born in 1923, proposed vast space habitats and energy-collecting structures that could support long-duration voyages, while Sagan, born in 1934, popularized ideas of humanity as a spacefaring species capable of eventually spreading across the stars. Their writings bridged the gap between imagination and practical science, inspiring generations of engineers, physicists, and dreamers to think seriously about what would once have seemed impossible. Even in the early 21st century, the spirit of these early ideas persisted. Proposals such as Breakthrough Starshot, announced in 2015, aim to send tiny, laser-propelled probes to the nearest star system, Alpha Centauri, within a human lifetime. This modern project embodies the lineage of thought that stretches from Jules Verne's canon to Tsiolkovsky's equations, Oberth's rocketry, and the nuclear propulsion studies of the 1950s. It demonstrates that the boundary between imagination and scientific possibility has continually shifted outward as technology advances. The ideas that once seemed like pure fantasy are gradually being translated into real proposals, even if practical interstellar travel for humans remains far in the future. The journey from early speculation to serious scientific study reveals much about the human mind and our persistent desire to reach beyond what seems immediately possible. At every stage, from ancient myths to modern proposals, humanity has combined imagination, curiosity, and scientific reasoning to stretch the boundaries of what can be conceived. The process illustrates how fiction can inspire science, and how careful analysis and experimentation can transform fantastical dreams into serious inquiries. Interstellar travel, while still beyond our technological reach, has become a legitimate field of study, reflecting humanity's enduring fascination with the stars. By tracing this evolution, one can see the power of ideas to shape exploration, the interplay of culture and technology, and the unyielding human desire to journey to places no one has yet visited. Even as the 21st century unfolds, the same themes persist. Each new advance in physics, propulsion, or material science opens small doors to the possibility of reaching nearby stars. Ideas that were once only imaginative stories are now considered in scientific workshops and journals, with engineers and theorists calculating trajectories, propulsion methods, and energy requirements. While practical interstellar travel for humans remains an enormous challenge, the path from science fiction to first scientific proposals demonstrates a remarkable continuity of thought, showing that what begins as imagination can, over time, become a blueprint for real exploration. The earliest ideas of interstellar travel, emerging from myths, stories, and speculation, have matured into a field where physics, engineering, and creativity intersect, hinting at a future in which humans may one day reach the stars just as we have always dreamed. The fascination with stars has never waned, and each generation of scientists and dreamers builds upon the work of those who came before. The early 20th century thinkers, inspired by the imaginative literature of the 19th century, laid the foundation for engineering and physics solutions that might one day make interstellar travel a reality. Even today, when concepts like warp drives or antimatter propulsion are explored in theoretical physics, they owe their origins to the early blend of science and imagination that first made humans consider that they might one day leave Earth behind. In this sense, the story of interstellar travel is not just about technology, rockets, or physics equations. It is about human curiosity, ambition, and the enduring drive to explore the unknown. Every speculative story, every equation, and every proposal represents a step toward a future where the stars are not just points of light in the night sky, but destinations within our reach. Humanity's fascination with the stars has always been accompanied by a sobering realization. Our current technology places strict limits on how far we can travel into the cosmos. The rockets that we have today, remarkable as they are, were originally designed for travel within our own solar system. They were conceived to lift humans and cargo into low Earth orbit, to send probes to the Moon, and even to journey to planets such as Mars. The speed they can achieve is impressive when measured in the context of Earth, but in the vastness of interstellar space it becomes painfully slow. The distances between stars are so enormous that even the fastest spacecraft we have ever built would require tens of thousands of years to reach the nearest star. For example, the closest star to Earth, Proxima Centauri, is about 4.22 light-years away. To put that into numbers that are easier to grasp, that is roughly 25 trillion miles, an almost unimaginable distance. The rockets of today, even those that travel the fastest, would take tens of thousands of years to traverse that span. This simple reality underlines one of the most stubborn obstacles facing humanity's dreams of leaving the solar system: propulsion. The rockets currently in use rely almost entirely on chemical propulsion. In a chemical rocket, fuel and oxidizer combine in a reaction that produces hot gas, which is then expelled out of the back of the rocket at high speed, pushing the craft forward. This principle, known as Newton's third law of motion, works brilliantly for lifting massive vehicles off Earth against the pull of gravity, but it has severe limitations when it comes to the vast emptiness of space. Chemical rockets produce enormous thrust, but their efficiency is relatively low. Efficiency in this context is measured by something called specific impulse, which roughly describes how much thrust you get for a given amount of fuel. Even the most advanced chemical rockets have a specific impulse that cannot approach the speeds needed for interstellar travel. To reach even a fraction of the speed of light, a chemical rocket would require an almost infinite amount of fuel, far beyond anything we could feasibly carry or produce. This fuel problem is not just about weight. The more fuel a rocket carries, the more mass it has to accelerate, which then requires even more fuel, creating a vicious cycle that quickly becomes impossible. This is why no one has seriously proposed sending a chemical rocket to another star. The problem is not a minor technical hurdle. It is a fundamental limitation of the method itself. Even when we consider the fastest spacecraft humanity has ever launched, the challenge becomes starkly clear. The Parker Solar Probe, launched in the year 2018, is currently the fastest human-made object relative to the Sun, reaching speeds of roughly 435,000 miles per hour. While this is astonishing compared to any previous mission, it is still only about 1/2000th of the speed of light. At this pace, it would take more than 6,000 years to reach Proxima Centauri. Such numbers make it obvious that current propulsion methods are inadequate for interstellar journeys, even if we were willing to wait many human lifetimes for the arrival. These examples highlight why scientists are forced to look beyond chemical rockets if humanity ever hopes to explore beyond our solar neighbourhood. Engineers and physicists have considered alternative propulsion methods that could, in theory, reach much higher speeds. But each of these methods comes with daunting challenges. One such idea is nuclear propulsion, which can take the form of nuclear thermal rockets or nuclear pulse propulsion. In a nuclear thermal rocket, a nuclear reactor heats a propellant such as hydrogen to extremely high temperatures, creating thrust when the hot gas is expelled. This method is far more efficient than chemical propulsion, and could allow spacecraft to reach significant fractions of the speed achievable by conventional rockets. Nuclear pulse propulsion, on the other hand, involves detonating small nuclear explosives behind a spacecraft to push it forward, a concept studied seriously in the 1950s and 60s under the codename Project Orion. While nuclear propulsion offers dramatic improvements over chemical rockets, it also faces immense technical and political hurdles. The creation, containment, and safe use of nuclear explosions in space remain fraught with risk, and international treaties restrict the use of nuclear weapons in space, further complicating the possibility of employing such technology. Another intriguing idea that has been studied extensively is ion propulsion. Ion engines accelerate charged particles to extremely high speeds using electric or magnetic fields, producing thrust much more efficiently than chemical rockets. Spacecraft such as the Dawn probe, which explored the asteroids Vesta and Ceres, have successfully used ion propulsion to gradually change orbit over long periods. While this technology is promising for in-system travel and could enable missions to distant planets, it still produces very little thrust compared to the enormous demands of accelerating a spacecraft to near-light speeds. Even ion engines, remarkable as they are, would take centuries or millennia to reach the nearest star, making them unsuitable for practical interstellar travel without major breakthroughs. The difficulties of interstellar propulsion are further magnified when we consider the energy requirements. Reaching even 10% of the speed of light, which is far slower than what would be ideal for human-scale interstellar travel, would require an amount of energy equivalent to the total energy consumed by humanity in many decades. Storing and managing such vast amounts of energy presents problems that are orders of magnitude beyond what current technology can handle. Additionally, the longer a spacecraft travels, the more it must contend with hazards such as collisions with tiny particles of dust and cosmic rays, which can cause damage over time. At speeds approaching a significant fraction of the speed of light, even particles smaller than a grain of sand can deliver energy comparable to that of a high-speed bullet, potentially destroying unshielded spacecraft. Chemical rockets, ion engines, or even nuclear propulsion systems would have to be paired with extraordinary protective measures, adding more weight and complexity to the already difficult challenge of interstellar flight. Concepts such as antimatter propulsion have been proposed to overcome these energy and efficiency problems, but these remain purely theoretical for the moment. Antimatter reactions, in which matter and antimatter annihilate each other, release enormous amounts of energy relative to mass, far surpassing chemical or nuclear reactions. In principle, a spacecraft fueled by antimatter could reach speeds approaching a significant fraction of light speed. The problem is that producing and storing antimatter is immensely difficult with current technology. Today, humans can only produce tiny amounts of antimatter in particle accelerators, far less than what would be needed for even a small interstellar mission. Moreover, antimatter must be stored in perfect isolation from ordinary matter, or it would annihilate immediately, making propulsion control extraordinarily complex and dangerous. While antimatter propulsion is a tantalizing concept that could, in theory, make interstellar travel feasible within human lifetimes, the engineering challenges are so severe that it is unlikely to be practical for many decades, if not centuries, unless revolutionary breakthroughs occur. Solar sails offer yet another approach to propulsion that bypasses traditional fuel limitations. A solar sail uses large reflective sheets to catch the pressure of sunlight or even powerful laser beams, gradually accelerating a spacecraft over time. This method can, theoretically, accelerate a craft to very high speeds without carrying fuel, as long as the sail can be kept large and light enough. Experiments such as the Japanese spacecraft Icaros, launched in 2011, have demonstrated the feasibility of solar sails within our solar system. However, even with laser-assisted propulsion from powerful Earth-based or orbital lasers, Reaching a nearby star would still take decades, and the engineering challenges of constructing and maintaining such systems remain formidable. The distances are so vast that even small deviations in trajectory could result in missing the target star by millions of miles, emphasizing the difficulty of controlling long-duration, high-speed interstellar missions. Beyond propulsion, other limitations compound the problem. Human travel, for instance, requires life support, radiation shielding, and food, all of which add significant mass to the spacecraft. The more mass a vehicle carries, the more thrust it requires, which in turn increases the energy and fuel needed. Robots, being lighter and more resilient, present a more feasible initial option for interstellar exploration, but even robotic missions face the same fundamental physics challenges of acceleration, deceleration, and energy supply. Current rockets, whether chemical, nuclear, or ion-based, were designed for operations within our own solar system, where distances are measured in millions of miles. Interstellar travel, by contrast, requires travelling across distances measured in trillions of miles, making conventional propulsion technology almost irrelevant. The practical reality is that, with current technology, interstellar travel is effectively impossible for human missions. While robotic probes might be able to reach nearby stars given enough time, human explorers face insurmountable hurdles in terms of speed, energy, and life support. Even the most optimistic projections suggest that a crewed mission to another star using conventional or near-future propulsion methods would take tens of thousands of years. In the history of human exploration, no journey has ever demanded such extreme scales of time and energy. The rockets that have taken astronauts to the moon, or robotic probes to the outer planets, are marvels of engineering and courage, but their capabilities are dwarfed by the cosmic distances that separate the stars. Understanding these limits is crucial for planning future space exploration. Scientists and engineers must either develop radically new propulsion methods or accept that interstellar travel will remain the domain of science fiction for the foreseeable future. The laws of physics, particularly those governing energy, mass, and motion, impose hard constraints that cannot be bypassed by incremental improvements to current technology. While dreams of interstellar voyages inspire innovation and imagination, the reality is that humanity's current rockets are firmly constrained to our solar system. Even if we can achieve modest increases in speed with advanced nuclear or ion propulsion, the sheer distances involved make the journey to even the nearest star a generational endeavour at best. Efforts to conceptualize interstellar travel have inspired extraordinary ingenuity. Scientists have proposed massive laser arrays to push ultralight spacecraft, swarm-based probes that operate collectively, and even theoretical warp drives that would bend space itself to reduce travel time. All of these ideas, however, remain far beyond what humanity can build today. The energy requirements, engineering challenges, and physical dangers are so extreme that they remain speculative. In contrast, the rockets we currently possess are tangible and proven, but they cannot overcome the fundamental barrier of distance. The universe is immense, and our technology is still in its infancy. Understanding the propulsion limits of current rockets is not a failure of imagination, but a recognition of the reality that space travel is a battle against immense distances and the unforgiving laws of physics. The idea of using nuclear power to propel a spacecraft has captured the human imagination for more than 70 years, ever since the development of atomic energy reshaped our understanding of what might be possible in space exploration. Long before modern interstellar travel theories and the ambitious dreams of sending humans to distant stars, scientists and engineers began imagining a new class of starships, ones powered not by chemical rockets that rely on burning fuel, but by the immense energy released from atomic reactions. The sheer thought of harnessing the power of the atom to push a ship through the emptiness of space was electrifying, promising speeds far beyond the limits of conventional rockets, and offering the hope that humanity might one day venture beyond our tiny solar neighbourhood. Nuclear propulsion promised a revolution, a way to escape the slow crawl imposed by chemical fuels and open up the universe in ways that seemed almost like magic. One of the earliest and most famous of these ambitious projects was Project Orion, a concept first seriously studied in the late 1950s and early 1960s. This audacious idea was to build a spacecraft propelled by a series of controlled nuclear explosions detonated behind the ship. The principle was both simple and terrifying. Small atomic bombs would be ejected from the rear of the spacecraft, and each explosion would produce an enormous blast of energy, pushing the ship forward with every detonation. A massive shock-absorbing plate at the back of the spacecraft would absorb the impact, converting the explosive force into smooth acceleration. The idea was unlike anything attempted before, combining raw nuclear power with a mechanical system designed to endure repeated blasts, and it captured the imagination of both scientists and the public. Designers envisioned enormous starships, far larger than anything humanity had ever built, carrying hundreds of people on journeys that could span entire star systems. In theory, Project Orion offered astonishing potential. A nuclear pulse-driven spacecraft could, in a single trip, reach speeds that chemical rockets could only dream of. Unlike chemical propulsion, which is limited by the relatively low energy density of fuel, nuclear explosions release millions of times more energy from a given mass of material. This meant that Orion could potentially carry heavy payloads or even large colonies of people to distant planets, making interstellar travel at least theoretically possible. Some designs calculated that a spacecraft using this method could reach a significant fraction of the speed of light, allowing trips to nearby star systems within a human lifetime. The optimism was grounded in serious physics, and the engineers behind the project explored every detail, from the timing of bomb detonations to the materials needed to survive repeated nuclear blasts. Despite its promise, Project Orion faced enormous practical and political challenges. The first and most obvious was safety. Detonating atomic bombs in space raised concerns not only about radiation, but also about legal and environmental consequences. The Partial Test Ban Treaty of 1963, which prohibited nuclear explosions in the atmosphere, underwater and in space, effectively ended the possibility of testing the Orion concept in the real world. In addition, the engineering challenges were daunting. Building a spacecraft that could withstand hundreds or thousands of atomic blasts without structural failure required materials and shock-absorbing technology that were far ahead of what existed at the time. Even if the physics was sound, the technical hurdles were immense and the costs were astronomical. Nonetheless, the project provided invaluable insights into what nuclear propulsion could achieve and inspired future generations of scientists and science fiction writers alike. While Project Orion is the most famous example, it was by no means the only idea for atomic-powered starships. In the decades that followed, scientists explored a wide range of nuclear propulsion concepts, each with its own unique approach to harnessing atomic energy for space travel. One major line of research was nuclear thermal propulsion, which relies on a nuclear reactor to heat a propellant, such as hydrogen, to extremely high temperatures before expelling it through a nozzle to produce thrust. Unlike Orion, which relied on explosive pulses, nuclear thermal rockets operate more like conventional engines but with vastly higher efficiency. In the 1950s and 60s, the United States developed the NERVA program, which built and tested nuclear thermal rocket engines capable of sustained operation. These engines could theoretically propel spacecraft to Mars or even the outer planets far faster than chemical rockets, offering a practical step toward human exploration of the solar system, while still relying on well-understood physics rather than uncontrolled nuclear detonations. Another intriguing concept is nuclear electric propulsion, which converts the energy from a nuclear reactor into electricity to power ion engines or other forms of electric thrusters. These systems generate far lower thrust than chemical or nuclear thermal rockets, but can operate continuously over years or decades, gradually accelerating a spacecraft to tremendous speeds. The advantage of this approach is its incredible fuel efficiency and the ability to undertake missions that would otherwise be impossible. Nuclear electric propulsion has been considered for deep space missions, such as sending robotic probes to the outer planets, asteroids, or even interstellar space. The concept is particularly appealing for missions requiring high-speed, long-duration travel, where carrying large amounts of conventional fuel would be impractical or impossible. It also represents a path toward nuclear-powered starships that could one day take humanity to the nearest stars. Over time, the scientific imagination expanded even further, exploring hypothetical propulsion methods that combine nuclear reactions with advanced concepts from physics. Ideas such as antimatter catalyzed nuclear explosions, where tiny amounts of antimatter would trigger powerful atomic reactions, promised even greater energy densities and potential speeds approaching significant fractions of the speed of light. While these concepts remain largely theoretical, they demonstrate the enduring appeal of nuclear propulsion as a way to overcome the immense challenges of interstellar travel. Every new idea builds on the realization that the fundamental limitation of conventional rockets, their reliance on chemical fuel, can be overcome by tapping into the far greater energy stored in atomic nuclei. Each proposed design stretches the boundaries of what is technologically conceivable, even if many are far from practical implementation today. In addition to scientific and engineering considerations, nuclear propulsion has always carried profound cultural and psychological weight. The image of a spaceship riding a series of atomic explosions evokes both awe and fear, highlighting the dual nature of nuclear energy as a tool for both creation and destruction. The fascination with these ideas reflects humanity's broader desire to master forces far larger than ourselves, to reach out into the cosmos and assert our presence among the stars. Writers of science fiction were quick to embrace these concepts, depicting enormous starships powered by nuclear engines, carrying explorers across unimaginable distances and encountering alien worlds. The stories inspired real engineers and physicists, creating a feedback loop between imagination and technical ambition that continues to this day. The lessons of Project Orion and other nuclear propulsion concepts extend beyond the engineering challenges. They force humanity to confront fundamental questions about risk, ethics, and ambition. Detonating nuclear devices in space or near other celestial bodies carries dangers not only to human crews, but also to potential ecosystems, satellites, and future space infrastructure. Balancing these risks against the potential rewards of rapid space travel has been a persistent theme in the history of nuclear propulsion research. Even as technology advances, the ethical and political dimensions remain complex. Discussions of nuclear-powered starships inevitably intersect with broader debates about the role of atomic energy in society, the militarization of space, and humanity's responsibility toward the cosmos. Despite decades of research, no nuclear propulsion system has yet been used to launch humans beyond low Earth orbit, and the dream of interstellar travel remains distant. Yet the ideas developed in the mid-20th century laid the foundation for modern thinking about space propulsion. Concepts such as nuclear thermal rockets and nuclear electric engines are still actively studied, with experimental and theoretical work continuing around the world. Advances in materials science, reactor design, and space engineering bring the possibility closer to reality, even if the technical and political hurdles remain formidable. The knowledge gained from past studies informs current proposals and renewed interest in deep space exploration, whether to Mars, asteroids, or eventually other star systems, keeps the spirit of atomic-powered starships alive. Humanity's fascination with nuclear propulsion also reflects our broader relationship with energy itself. Chemical rockets, though sufficient for reaching the Moon and Mars, are fundamentally limited by the energy density of their fuel. By contrast, atomic reactions release millions of times more energy per unit mass, offering a glimpse of what might be possible if we can master the technology. The dream of nuclear-powered starships is a story about ambition, curiosity, and the desire to transcend our current limitations. It is a reminder that the universe is vast, that the distances between the stars are immense, and that achieving meaningful travel across these distances requires not only imagination, but also courage, ingenuity, and patience. Exploring the history of nuclear propulsion also reveals the interplay between science, politics, and culture. During the Cold War, atomic energy symbolized both promise and peril, and ambitious projects like Orion were pursued in an environment of intense competition and technological optimism. Scientists worked alongside the military, imagining a future in which humanity could harness the most powerful forces in the universe. The constraints of treaties, public opinion, and technological feasibility ultimately curtailed many of these dreams, but the conceptual breakthroughs endured. Today, engineers and researchers continue to draw inspiration from these early projects, using them as a benchmark for what might one day be achieved when the technical, political, and ethical conditions align. The story of nuclear propulsion also highlights the gradual progression of human technological capabilities. In the 1950s, materials science, electronics, and reactor design were still in their infancy. Proposals like Orion tested the limits of what was theoretically possible, often stretching beyond what could be realistically built. Modern technology, including advanced computer modelling, sophisticated materials, and precise control systems, makes some aspects of these ideas more feasible than they once were. Concepts that seemed fantastical decades ago now appear as serious candidates for future exploration, albeit with continued challenges in safety, economics, and environmental protection. Every incremental advance brings humanity closer to the possibility of constructing vessels capable of travelling far beyond our solar system. The variety of nuclear propulsion concepts developed over the years demonstrates the creativity and persistence of scientists and engineers. From the dramatic pulse-driven designs of Project Orion to the steady, efficient thrust of nuclear thermal and electric engines, each approach represents a different strategy for converting the immense energy of atomic nuclei into motion through space. Each concept carries its own advantages and limitations, reflecting the trade-offs between speed, efficiency, payload capacity, and risk. The continued exploration of these ideas underscores the enduring allure of nuclear power as a key to unlocking the stars and points to the breadth of human ingenuity in confronting one of the most formidable challenges imaginable: reaching other worlds across the vast emptiness of interstellar space. Even today, as commercial space ventures expand and new propulsion technologies emerge, the legacy of atomic-powered starship concepts remains influential. The fundamental problem of interstellar travel, the enormous distances involved and the energy required to traverse them, continues to shape research and inspire innovation. Nuclear propulsion offers one of the few realistic pathways to achieving the high speeds necessary for deep space missions. By examining the successes, failures, and unrealized potential of past projects, scientists gain a clearer understanding of what is feasible and what might require breakthroughs yet to come. The lessons learned from decades of research on nuclear propulsion inform not only spacecraft design, but also our broader understanding of how humanity might extend its presence into the cosmos. Project Orion, nuclear thermal rockets, and nuclear electric propulsion all share a common theme: the need to confront the fundamental limitations imposed by conventional energy sources and to imagine new ways to harness the immense power of the atom. They reflect a willingness to think boldly, to pursue ideas that at first seem impossible, and to take calculated risks in the pursuit of knowledge and exploration. The vision behind these projects is not merely about speed or distance. It is about redefining humanity's relationship with the universe, transforming us from inhabitants of a single small planet into explorers capable of reaching the stars. These ideas challenge us to consider what we value, what we are willing to risk, and how far we are prepared to go to achieve our dreams of interstellar adventure. The conceptual elegance of nuclear propulsion is matched by its potential practical impact. For instance, a nuclear thermal spacecraft could cut travel times to Mars by half or more compared to chemical rockets, making human missions more feasible and reducing the risks associated with long-duration spaceflight. Similarly, nuclear electric propulsion could enable missions to the outer planets and beyond, supporting scientific exploration, resource utilization, and perhaps even the initial steps toward permanent human presence beyond Earth. The promise of these technologies lies not only in reaching distant destinations, but also in transforming the way humans think about space, energy, and the possibilities of the future. By pushing the boundaries of what is physically possible, nuclear propulsion challenges us to expand our imagination as much as our engineering capabilities. Nuclear-powered starship concepts also serve as a bridge between science fiction and scientific reality. Authors in the mid-20th century, inspired by projects like Orion, envisioned vast fleets of atomic-powered vessels exploring distant star systems, carrying entire human civilizations across the galaxy. These imaginative works did more than entertain. They shaped public perception, inspired future scientists, and created a cultural context in which interstellar travel became a plausible goal rather than a mere fantasy. The interplay between fiction and engineering continues today, as concepts once considered science fiction slowly move toward potential realization through advances in physics, materials, and reactor technology. The story of nuclear propulsion is thus a story about the power of ideas, the feedback loop between imagination and invention, and the human drive to explore the unknown. As humanity looks to the future, the potential for nuclear propulsion remains both tantalizing and challenging. Projects like Orion remind us of what is theoretically possible when bold thinking meets rigorous engineering, even if practical implementation remains distant. Nuclear thermal and electric propulsion provide more immediate pathways for near-term missions, offering the possibility of faster, more efficient travel within the solar system. At the same time, advanced and speculative concepts hint at even greater possibilities, suggesting that one day humanity may harness atomic power in ways we have only begun to imagine, enabling journeys to the nearest stars. The continued study of these ideas ensures that nuclear propulsion remains a central part of our vision for the future of space exploration, symbolizing both the extraordinary potential and the profound responsibility that comes with wielding the power of the atom. The enduring appeal of nuclear-powered starships is a reflection of humanity's broader aspirations. We seek to move beyond the limitations of our home planet, to extend our reach into the cosmos, and to understand our place in the universe. By studying, imagining, and developing nuclear propulsion concepts, scientists and engineers explore the limits of technology while confronting fundamental questions about energy, ethics, and the future of human civilization. The story of Project Orion and its successors is a story of audacity, creativity, and the relentless pursuit of knowledge, demonstrating how the desire to explore can drive innovation and inspire generations. It is a reminder that even the most ambitious dreams, once considered impossible, can leave a lasting impact on science, culture, and the collective imagination of humanity. From the first sketches of Orion's shock-absorbing plate to the complex calculations of nuclear thermal and electric engines, the evolution of atomic-powered starship concepts reflects a unique intersection of physics, engineering, and imagination. Every attempt, whether successful, theoretical, or unrealized, contributes to our understanding of what is possible and what challenges remain. The vision of harnessing nuclear energy to propel humanity across the stars is not just a technical pursuit. It is a reflection of our enduring curiosity, our willingness to confront danger and uncertainty, and our desire to reach for what lies beyond the known. By continuing to study these ideas, we keep alive the possibility that one day humans may leave the solar system behind, venturing outward into the vast, mysterious, and awe-inspiring expanse of the galaxy. Ultimately, nuclear propulsion embodies the dream of interstellar travel in its most visceral form. It is the promise of using the most powerful energy known to humanity to overcome the seemingly insurmountable distances of space. The stories, designs, and theories developed since the 1950s continue to resonate because they speak to the core of what it means to explore, to dream boldly, to calculate meticulously, and to take the first steps toward a future that may lie among the stars. Even as we confront the technical, political, and ethical obstacles, the legacy of Project Orion and other nuclear-powered starship concepts endures, reminding us that the pursuit of knowledge and the desire to explore are among the most powerful forces driving human progress. The imagination, ingenuity, and determination that fueled Project Orion, nuclear thermal propulsion, and nuclear electric propulsion illustrate the unique blend of creativity and scientific rigor that defines humanity's approach to space exploration. Every calculation, every theoretical model, and every design proposal represents a step toward understanding how we might harness atomic energy to achieve extraordinary feats. The lessons learned from these projects inform current efforts in space propulsion, inspire new generations of engineers and scientists, and keep alive the hope that one day humanity might travel not just to nearby planets, but to distant star systems. Nuclear propulsion, with all its challenges and possibilities, remains a testament to human ambition, a symbol of our desire to reach beyond the confines of Earth and touch the stars themselves. The concepts developed under the banner of nuclear propulsion reflect an enduring vision of what human civilization might become. They envision starships capable of carrying entire populations, sustaining life over decades or centuries, and travelling across interstellar distances once thought unimaginable. These ideas are not merely exercises in physics, they are explorations of human potential, blending scientific understanding with audacious ambition. From the detonation-driven pulse engines of Project Orion to the efficient, continuous thrust of nuclear electric drives, each concept demonstrates that the path to the stars requires both imagination and rigorous engineering. The legacy of these ideas continues to shape the way we think about propulsion, energy, and the ultimate destiny of humanity among the stars. The excitement surrounding nuclear-powered starship concepts also stems from the enormous scale of what is possible. A pulse-driven Orion spacecraft could, in principle, be the size of a city, capable of carrying thousands of people, enormous scientific equipment, and vast supplies, all propelled by a technology that harnesses the power of the atom. The magnitude of these concepts stretches the mind, revealing the gulf between the small, fragile human experience on Earth and the vast, uncharted expanses of space. Even if practical implementation remains elusive, the conceptual daring of nuclear propulsion projects continues to inspire, illustrating that human ingenuity is not limited by present technology, but propelled by vision, ambition, and the relentless curiosity that drives exploration. Humanity's exploration of nuclear propulsion is not only a technical story, but also a philosophical one. It forces us to grapple with the immense power we have unlocked and consider how best to wield it responsibly. The promise of rapid space travel comes with equally profound responsibilities, including environmental stewardship, safety, and ethical use of nuclear energy. The history of projects like Orion and ongoing research into nuclear thermal and electric propulsion reminds us that progress is intertwined with responsibility. Every new advance in propulsion technology challenges us to balance ambition with caution, imagination with practical wisdom, and desire with foresight. The pursuit of atomic-powered starships is, therefore, a reflection of both human aspiration and human conscience, a testament to our capacity to dream and to act thoughtfully in the face of extraordinary possibilities. From the early experiments with small nuclear reactors to the complex designs for starships capable of interstellar travel, the story of nuclear propulsion illustrates the evolution of human thinking about energy and exploration. It reveals how bold ideas can persist, evolve, and inspire even in the face of technical obstacles, political limitations, and ethical dilemmas. The concepts developed over the past 70 years provide not only technical insights, but also a cultural framework for imagining humanity's future in space. They remind us that the dream of leaving our solar system, once considered science fiction, is now a serious scientific and engineering pursuit, guided by lessons learned from past experiments, theoretical breakthroughs, and visionary thinking. The journey from Project Orion to modern nuclear propulsion research reflects an ongoing commitment to expanding the horizons of human possibility and a persistent hope that one day humanity may ride the power of the atom into the stars themselves. The dream of travelling beyond our solar system has fascinated humans for centuries, filling our stories, our imaginations, and our scientific aspirations with visions of distant stars and unknown worlds. For as long as humanity has looked up at the night sky, the twinkling points of light have seemed tantalizingly close and yet unreachable. The idea of travelling to those distant suns, to worlds circling them, has always been a question of how we might harness energy and propulsion, powerful enough to bridge the enormous distances involved. One of the most promising ideas that has captured the attention of scientists, engineers, and science fiction writers alike is the concept of fusion-powered starships. Unlike the chemical rockets that have carried humans to the moon and robots across the solar system, fusion offers a glimpse of a future in which interstellar voyages might become possible, powered by the same processes that energize stars themselves. Fusion is the process by which lighter atomic nuclei, such as hydrogen, combine under extreme pressure and temperature to form heavier nuclei, releasing enormous amounts of energy. This is the very process that powers our Sun, where hydrogen nuclei fuse to form helium, creating the light and heat that sustain life on Earth. On Earth, humans have long sought to replicate fusion, initially for weapons in the form of hydrogen bombs, but later for peaceful energy production. The potential of fusion as a source of energy is staggering, offering a fuel that is abundant, relatively safe, and capable of producing immense power without the radioactive waste of traditional nuclear fission. For a starship, the appeal of fusion is even greater. The energy density of fusion is so high that a small amount of fuel could, in principle, propel a spacecraft to a significant fraction of the speed of light, opening up the possibility of reaching nearby stars within a human lifetime. The concept of a fusion-powered starship has a long and storied history. In the mid-20th century, during the height of the space race and the early years of nuclear experimentation, scientists began seriously considering how controlled fusion reactions could be harnessed for space travel. One of the earliest proposals was known as Project Dedelus, which was developed by the British Interplanetary Society in the 1970s. The design envisioned an unmanned probe that could reach Barnard's star, a red dwarf located approximately 6 light-years away from Earth, within a mere 50 years. This was ambitious by any standard, considering that the fastest spacecraft humans had launched at the time would have taken tens of thousands of years to reach such a destination. Project Dedelus proposed using a series of fusion micro-explosions, where pellets of deuterium and helium-3 would be ignited in a controlled manner to produce thrust. The spacecraft would be enormous, nearly 200 meters long, and would carry thousands of tons of fuel, yet it promised speeds up to 12% of the speed of light, making interstellar travel theoretically feasible for the first time. The technical challenges of fusion propulsion are immense. Producing a controlled, sustained fusion reaction on Earth has proven extraordinarily difficult, despite decades of research and investment. Fusion requires temperatures of millions of degrees, pressures comparable to the core of stars, and precise containment to prevent the reaction from dissipating. On Earth, devices such as tokamaks and inertial confinement reactors have achieved brief moments of fusion, but maintaining a continuous reaction that produces more energy than it consumes, known as ignition, remains elusive. For a starship, these challenges are compounded by the need to operate safely in the vacuum of space, to manage the immense heat produced, and to convert the energy of fusion into directed thrust efficiently. The idea of carrying thousands of tons of fuel, shielding the crew and electronics from radiation, and controlling repeated micro-explosions is not merely engineering, it is a profound leap in technological mastery. Despite these obstacles, the potential advantages of fusion propulsion are transformative. Chemical rockets, like those that carried humans to the moon, are limited by the energy contained in chemical bonds. They can reach impressive speeds within the solar system, but are utterly inadequate for interstellar travel. Even the most powerful chemical rockets would take tens of thousands of years to reach the nearest stars. Fusion, by contrast, offers energy densities thousands of times greater than chemical fuels. A spacecraft fueled by deuterium and helium-3 could, in principle, reach speeds approaching a significant fraction of the speed of light, reducing travel time to a few decades for nearby stars. This shift is not just a matter of convenience, it changes the very nature of human exploration. For the first time, we could envision missions that extend beyond the solar system, carrying probes, instruments, and eventually humans to distant stellar systems. One of the most intriguing ideas for fusion propulsion involves the use of helium-3, a rare isotope of helium that is scarce on Earth, but may be more abundant on the Moon and in the atmospheres of the giant planets. Helium-3 is particularly attractive because fusion reactions involving deuterium and helium-3 produce charged particles rather than neutrons, which can be directed using magnetic fields to produce thrust efficiently. This form of propulsion, sometimes called direct fusion drive, has the advantage of minimizing radioactive contamination and maximizing thrust-to-weight ratios. In principle, a fusion starship using deuterium-helium-3 reactions could accelerate continuously for years, coast through interstellar space, and decelerate upon arrival at a target star system, all while carrying a manageable amount of fuel. The prospect of mining helium-3 from extraterrestrial sources adds another layer of complexity and excitement, connecting fusion propulsion to the broader story of humanity becoming a spacefaring species. Beyond Project Dedelus, other proposals have emerged, each exploring different ways to harness fusion for interstellar travel. Project Longshot, developed by the United States in the 1980s, envisioned an unmanned fusion-powered probe sent to Alpha Centauri, the closest star system to Earth, which is approximately 4.3 light-years away. Longshot would have carried a compact nuclear reactor to provide power for guidance and communications, while the main propulsion came from deuterium-helium-3 fusion. Like Dedelus, Longshot would rely on a series of controlled fusion explosions to achieve high velocities, demonstrating the recurring theme that controlled, repeatable fusion reactions could be the key to reaching other stars. Another concept, called the inertial fusion rocket, focuses on using small pellet-sized fuel elements ignited by lasers or particle beams to produce thrust. This approach builds on developments in inertial confinement fusion on Earth, where powerful lasers compress and heat small pellets of fuel to initiate fusion. Scaling this technology to space travel would involve creating a system capable of firing thousands of pellets per second, each producing a tiny but cumulative burst of thrust. The advantage of this approach is precision and control. The spacecraft could adjust its trajectory and acceleration in real time, responding to obstacles or navigation requirements during its long journey through interstellar space. Fusion propulsion is not limited to theoretical spacecraft or unmanned probes. The idea of sending humans to other star systems, though still far beyond our current capabilities, remains a guiding vision for much of the research in this area. Human missions pose additional challenges, including life support, radiation shielding, and the psychological effects of decades-long journeys in confined space. Nevertheless, the promise of fusion is that it could make such missions conceivable. A fusion-powered starship could accelerate at a steady rate for years, reaching a high fraction of the speed of light, then decelerate upon approach to a target system. In contrast to chemical propulsion, which would leave a human crew stranded in space for millennia, fusion opens the door to journeys that are long but survivable within a human lifespan. One cannot ignore the potential societal and economic implications of fusion-powered interstellar travel. Developing the technology to achieve controlled fusion for propulsion could have profound consequences on Earth as well. Fusion energy has long been seen as the holy grail of clean, virtually limitless power. Achieving it for spaceflight would likely accelerate progress in terrestrial fusion power plants, revolutionizing the energy landscape, reducing dependence on fossil fuels, and mitigating climate change. Moreover, the pursuit of fusion-powered starships would drive innovation in materials science, magnetic confinement, superconductivity, and robotics, creating technologies that would have far-reaching applications both in space and on Earth. The challenges of interstellar distances, however, remain daunting. The nearest star, Proxima Centauri, lies approximately 4.2 light-years away. Even travelling at 20% of the speed of light, a spacecraft would take more than 20 years to reach it. Speeds approaching such fractions of light require not only immense energy, but also precise navigation and protection against the hazards of interstellar space, including cosmic rays, micrometeoroids, and the unknown phenomena of the interstellar medium. Fusion propulsion could provide the sustained acceleration needed to reach these speeds. But even with such technology, interstellar travel is a venture of extreme commitment and complexity. Recent developments in fusion research on Earth provide a tantalizing glimpse of the future. Experiments at facilities such as the International Thermonuclear Experimental Reactor, located in France, and the National Ignition Facility in the United States, have achieved significant milestones towards sustained fusion reactions. While these experiments are focused on energy production, rather than propulsion, the underlying physics is the same. Achieving controlled ignition and net positive energy output is the critical first step toward creating reactors that could one day power starships. The progress made over the past decades suggests that what once seemed like science fiction is gradually moving toward the realm of feasible engineering. The allure of fusion-powered starships is not purely technological, it is deeply philosophical and aspirational. Humanity has always sought to explore, to push boundaries, and to understand its place in the cosmos. The stars, distant yet beckoning, have served as our ultimate destination. Fusion propulsion represents not just a means of travel, but a bridge to the unknown, a tool that could carry us to the threshold of other worlds. By harnessing the power of the stars themselves, we would become participants in the grand cosmic dance, capable of venturing to places that have existed only in our imagination for millennia. In addition to propulsion, fusion reactors aboard starships could provide life support and power for onboard systems. The immense energy produced could sustain artificial gravity through centrifugal systems, power advanced environmental controls, and provide radiation shielding for crews and sensitive electronics. Unlike chemical propulsion, which requires carrying vast quantities of fuel and provides limited energy for onboard systems, fusion offers a compact, long-lasting power source. The ability to generate energy continuously over decades would be essential for long-duration missions, enabling communication with Earth, operation of scientific instruments, and maintenance of spacecraft systems. Another exciting possibility is the integration of fusion propulsion with other advanced technologies. Concepts such as magnetic sails, which use magnetic fields to interact with interstellar plasma, could complement fusion drives by providing additional acceleration or deceleration. Similarly, advanced autonomous systems, artificial intelligence, and robotics could manage fusion reactors, monitor spacecraft systems, and perform scientific observations during long journeys, reducing the burden on human crews and increasing mission resilience. The combination of fusion power and intelligent automation paints a picture of starships that are self-sufficient, durable, and capable of navigating the interstellar void with precision and safety. Despite the challenges, the conceptual designs of fusion starships inspire both engineers and dreamers. Project Dedelus, Project Longshot, and other theoretical studies demonstrate that, with sufficient technological development, reaching other stars is not forbidden by the laws of physics. The limitations are practical: energy generation, fuel acquisition, reactor control, materials engineering, and human factors. Yet the gradual progress in fusion research and spacecraft design suggests that these challenges, while formidable, are not insurmountable. Every breakthrough in plasma confinement, superconducting magnets, or energy efficiency brings the dream of interstellar travel a little closer to reality. The journey to building a fusion-powered starship is as much a journey of human ingenuity as it is a technical endeavour. It requires decades, if not centuries, of sustained effort, international collaboration, and visionary thinking. The road is likely to be incremental, with smaller fusion-powered spacecraft serving as testbeds for propulsion concepts, followed by increasingly ambitious missions. The lessons learned along the way would not only pave the path to the stars, but also transform life on Earth, ushering in an era of abundant energy and unprecedented technological capability. The story of fusion-powered starships is ultimately a story of hope, persistence, and imagination. It is a vision of what humanity could achieve when it dares to reach for the stars, a vision that blends the elegance of physics with the audacity of human ambition. Each step forward in fusion research, each improvement in materials science, each refinement of spacecraft design brings the distant suns a little closer. While the practical realization of interstellar travel may still lie decades or even centuries in the future, the principles are understood, the concepts are solid, and the dream remains alive. Humanity's longing for the stars, combined with the promise of fusion energy, offers the tantalizing possibility that one day we will truly journey to the realms of other suns, exploring worlds that have until now existed only in the light of our imagination. Fusion-powered starships, therefore, are not merely theoretical constructs. They are the embodiment of human curiosity, creativity, and courage. They represent a path forward to the stars, grounded in the known laws of physics yet propelled by our insatiable desire to explore. The challenges ahead are extraordinary, yet history teaches that human ingenuity often rises to meet even the most daunting obstacles. By continuing to pursue controlled fusion, to experiment with propulsion concepts, and to dream boldly, humanity keeps alive the hope that one day we will cross the threshold of our solar system and reach the distant beckoning stars. In doing so, we would not only expand the horizon of human experience but also affirm our place in the vast and ever-unfolding cosmos, proving that the desire to explore, to learn, and to journey beyond the familiar is as fundamental to our nature as the stars themselves. The legacy of fusion-powered starships will ultimately be measured not only in kilometers travelled or light-years crossed, but in the expansion of knowledge, the advancement of technology, and the inspiration it provides to generations to come. The dream of harnessing the power of the stars to reach other stars is no longer a flight of fancy. It is a challenge to the human spirit, an invitation to turn the impossible into the achievable. With patience, persistence, and imagination, the age of interstellar exploration may one day dawn, powered by the boundless energy of fusion, and humanity may finally step out into the galaxy, carrying the hope, curiosity, and determination that have always defined us. Antimatter propulsion is one of the most fascinating and tantalizing ideas humanity has ever conceived when it comes to space travel. It represents a dream so powerful that it seems almost like science fiction made real, a vision of ships propelled not by chemical rockets or even nuclear reactions, but by the annihilation of matter and antimatter, releasing unimaginable amounts of energy. The very idea of antimatter is itself extraordinary. every particle of ordinary matter has a corresponding antiparticle, identical in mass but opposite in charge. For instance, the electron, which carries a negative electric charge, has a counterpart called the positron, which carries a positive charge. When a particle and its antiparticle meet, they annihilate each other completely, transforming their entire mass into pure energy, according to Einstein's famous equation, E=mc². This process releases energy on a scale far beyond what any conventional fuel could achieve. 1 gram of antimatter annihilating with 1 gram of ordinary matter would produce energy equivalent to about 43,000 tons of TNT, an amount that dwarfs even the largest thermonuclear bombs ever detonated on Earth. To put this into perspective, the atomic bomb that devastated Hiroshima in 1945 had a yield of approximately 15 kilotons of TNT, which is roughly 3,000 times less than the energy produced by just 1 gram of antimatter colliding with 1 gram of matter. The theoretical efficiency of antimatter propulsion is what makes it so alluring. Unlike chemical rockets, which convert only a tiny fraction of their fuel into usable energy, antimatter annihilation converts nearly 100% of the mass involved into energy, even compared with nuclear fission, which transforms roughly 1/10 of 1% of its fuel mass into energy, and nuclear fusion, which converts a few percent. Antimatter propulsion is unmatched. In practical terms, this means that a spacecraft powered by antimatter could, at least theoretically, reach a significant fraction of the speed of light. Imagine a vessel capable of travelling at 10%, 20%, or even 50% of the speed of light. Journeys to the nearest stars, which would otherwise take tens of thousands of years with current technology, could become achievable in decades or even a few years. The implications for interstellar travel are staggering. Human exploration could extend far beyond our solar system, opening up possibilities to visit planets orbiting nearby stars, study alien systems in detail, and even carry the seeds of life across vast distances. Despite its theoretical brilliance, antimatter propulsion is riddled with enormous challenges, some of which are almost inconceivable in scale. The first and most immediate difficulty lies in the production of antimatter. On Earth today, antimatter is created in particle accelerators, devices that smash particles together at incredible speeds, producing tiny amounts of antiparticles in the process. The problem is that the quantities produced are infinitesimally small. Modern particle accelerators can generate only a few nanograms of positrons or antiprotons per year, at enormous financial cost. To fuel even a modest antimatter spacecraft, trillions of times more antimatter would be required. For instance, a starship capable of a one-way journey to Proxima Centauri, the closest star to our Sun at a distance of approximately 4.2 light-years, might need several kilograms of antimatter. Producing that amount with current technology would take many thousands of years and cost quadrillions of dollars. This enormous discrepancy between the tiny amounts of antimatter we can currently generate and the huge quantities needed for propulsion underscores just how far our technology would have to advance to make antimatter-powered interstellar travel even remotely feasible. Beyond production, storing antimatter safely presents another monumental challenge. Because antimatter annihilates instantly upon contact with ordinary matter, it cannot be stored in conventional containers. Any contact with the walls of a container or stray particles of air would result in a violent release of energy. To prevent such catastrophic events, scientists have developed methods using electromagnetic traps, known as penning traps, which suspend charged antiparticles in a vacuum using magnetic and electric fields. These systems work for tiny amounts of antimatter, like a few billionths of a gram, but scaling them up to hold kilograms of antimatter needed for interstellar travel is a problem that currently defies engineering. The slightest imperfection, a fluctuation in the magnetic field, or a particle of dust could lead to an explosion powerful enough to destroy a city. Imagine trying to build a fuel tank for a spacecraft that holds a substance capable of detonating with a force thousands of times greater than any bomb humanity has ever created. The engineering precision, safety protocols, and redundancy required are almost beyond comprehension. The energy released by antimatter annihilation is not only immense but also extremely difficult to control. When a particle meets its antiparticle, the energy is often released in the form of high-energy gamma rays, which are notoriously difficult to direct. These gamma rays could damage the spacecraft, harm astronauts, or even make propulsion inefficient if not properly harnessed. Scientists have theorized several ways to convert this energy into thrust. One idea is to use the gamma rays to heat a working fluid, like hydrogen, to produce a jet of plasma that could be expelled to generate thrust. Another concept involves magnetic nozzles that can direct charge particles, such as antiprotons annihilating with protons, to produce directional force. Even with these concepts, converting the raw energy of antimatter annihilation into controlled propulsion with high efficiency remains purely theoretical. The challenges of energy management, shielding the crew and instruments, and preventing catastrophic failure create an almost perfect storm of technological hurdles. The very speed at which an antimatter-powered spacecraft could theoretically travel introduces additional complications. At significant fractions of the speed of light, even tiny particles of interstellar dust can become deadly projectiles, capable of puncturing a spacecraft and damaging critical systems. To survive these hazards, a starship would require robust shielding, which adds mass and complexity. Moreover, at speeds approaching light speed, relativistic effects become significant. Time would pass more slowly for the travelers compared with people remaining on Earth, a phenomenon predicted by Einstein's theory of special relativity. Communication back to Earth would be increasingly delayed, and navigational calculations would need to account for time dilation, interstellar radiation, and the gravitational influence of stars and planets along the journey. The idea of travelling so quickly across such vast distances is exhilarating, yet it brings with it a host of new physics and engineering problems that must be solved before any practical application becomes possible. Even if production, storage, and propulsion challenges were somehow overcome, the cost of an antimatter starship would be astronomical in every sense of the word. The creation of kilograms of antimatter alone would require infrastructure and energy generation on a scale that humanity has never attempted. Particle accelerators capable of producing grams of antimatter might need to consume more energy than the entire world produces in a year. The cost in materials, construction, and safety systems could easily reach hundreds of quadrillions of dollars. Funding such a project would require unprecedented international collaboration, the mobilization of resources comparable to or exceeding those used in the Apollo program, and a political will spanning decades or even centuries. Even the most optimistic projections place practical antimatter propulsion decades or centuries away, assuming continuous technological breakthroughs in energy production, particle physics, and materials science. Despite these staggering obstacles, antimatter propulsion remains a topic of intense scientific interest because of its unparalleled potential. In theory, it could allow humanity to explore the galaxy in ways previously unimaginable. Stars that seem impossibly distant, like Alpha Centauri, Barnard's star, and the more distant Wolf 350 light-years away, could be reached within human lifetimes if antimatter propulsion became feasible. This possibility has inspired generations of scientists, engineers, and dreamers to pursue the underlying physics and develop incremental technologies that might one day contribute to a practical system. Research into antimatter is not purely speculative. It has practical applications in medical imaging, such as positron emission tomography, and in high-energy physics experiments that probe the fundamental nature of matter. These incremental advances keep alive the hope that one day the extreme efficiency of antimatter could be harnessed for interstellar exploration. The broader implications of antimatter propulsion extend beyond mere speed. A spacecraft powered by antimatter could carry larger payloads than traditional propulsion systems, potentially enabling the transportation of habitats, scientific instruments, and even humans in numbers sufficient for long-term colonization of other star systems. Unlike chemical rockets, which are limited by the energy density of their fuel, antimatter systems could drastically reduce the amount of propellant needed for a given mission, allowing more room for life support systems, shielding, and scientific equipment. In addition, antimatter propulsion could fundamentally change the way humanity approaches exploration. Instead of slow, incremental missions that take centuries to reach even the nearest stars, antimatter-powered ships could make the interstellar frontier accessible on human timescales, transforming science fiction dreams into scientific goals. It is worth noting that antimatter propulsion has inspired a variety of theoretical designs, each addressing different aspects of the immense challenges involved. Some concepts focus on using antiprotons, which interact strongly with ordinary matter, providing a high density of energy release suitable for driving a rocket. Others consider positrons, which are lighter and easier to manipulate but produce energy primarily in the form of gamma rays that are harder to convert into thrust. Hybrid systems have also been proposed, combining antimatter with more conventional fusion or fission processes to improve safety, control, and overall efficiency. Each design comes with trade-offs between energy density, safety, control, and technical feasibility, reflecting the complexity and interrelated nature of the challenges in turning antimatter propulsion from a theoretical marvel into a practical technology. Safety remains a paramount concern in any antimatter endeavour. The consequences of even a minor containment failure could be catastrophic, releasing energy equivalent to many nuclear bombs in an instant. This necessitates redundant containment systems, active monitoring, emergency shutoffs, and potentially even autonomous systems capable of reacting faster than human operators. In addition, the radiation produced by antimatter annihilation poses a risk not only to the crew, but also to the electronics, requiring advanced shielding materials, magnetic deflection systems, or other methods to protect sensitive equipment. These requirements push the boundaries of materials science, electronics, and robotics, highlighting the multidisciplinary nature of the challenge. Developing antimatter propulsion is not merely a question of physics. It is a grand engineering problem that touches almost every field of modern science. The potential military and strategic implications of antimatter technology cannot be ignored either. The energy released by even small amounts of antimatter is so large that it could theoretically be weaponized. This dual-use nature complicates research, as governments may impose strict controls on antimatter production, storage, and transport, slowing civilian space applications. Ethical and legal questions would also arise regarding the deployment of such a powerful technology, both in space and on Earth. Balancing the incredible promise of antimatter propulsion with the risks it entails is a challenge not only for scientists and engineers, but also for policymakers and international organizations tasked with ensuring the safe development of advanced technologies. Despite these challenges, the pursuit of antimatter propulsion continues to captivate the imagination because it represents the ultimate energy source for space travel. Even incremental advances in antimatter research have the potential to benefit multiple fields, from medicine to fundamental physics. The quest to understand and control antimatter pushes the limits of human knowledge, inspiring innovations in particle physics, vacuum technology, magnetic confinement, and energy conversion. Each small step forward brings humanity closer to the possibility of one day creating a propulsion system that could take us beyond our solar system, across interstellar space, and perhaps even to other galaxies. The dream is vast, the obstacles daunting, and the rewards unimaginably great. Antimatter propulsion is not merely a technical challenge, it is a symbol of human ambition, curiosity, and determination. The idea that we could harness the annihilation of matter and antimatter to propel a ship through the cosmos represents a fundamental shift in how we think about energy, space, and our place in the universe. The obstacles are almost incomprehensible, from producing kilograms of antimatter to storing it safely, from converting its energy into usable thrust to shielding humans from the deadly radiation it produces. Yet the potential rewards are equally staggering. A successful antimatter-powered spacecraft could travel faster, farther, and more efficiently than any system conceived so far, making the stars accessible on timescales that are meaningful to human life. It is a technology that challenges every limit of physics, engineering, and imagination, and it remains a dream that drives scientific inquiry, fuels space exploration ambitions, and sparks the imagination of generations. Humanity has always been driven by the desire to explore, to push boundaries, and to reach beyond what was previously thought possible. Antimatter propulsion represents the extreme embodiment of that desire. The challenges are not only enormous but almost unimaginable in their scale and complexity, encompassing energy production, storage, containment, safety, engineering, and international cooperation. Yet the potential to convert mass into energy with near-perfect efficiency, to reach the stars in a human lifetime, and to carry significant payloads across interstellar distances makes the pursuit of antimatter propulsion a goal worthy of the greatest minds and boldest ambitions. It is a vision that reminds us that the universe is vast, our current technology is limited, but the possibilities, if we dare to pursue them, are almost limitless. It is the dream of converting the very fabric of matter into a cosmic vehicle, a dream that may one day transform science fiction into reality, taking humanity to the farthest reaches of the galaxy and beyond. The exploration of antimatter as a propulsion source also opens up philosophical and existential questions about humanity's place in the cosmos. If we could master such a powerful form of energy, we could not only traverse the stars but potentially encounter other civilizations, understand the formation of galaxies, and witness the universe on scales and timescales that are currently beyond our comprehension. Each theoretical breakthrough, each incremental improvement in particle confinement, production, or energy conversion carries with it the promise of expanding our understanding of reality itself. Antimatter propulsion is, in essence, a tool not just for travel, but for the expansion of human knowledge, offering the potential to explore both the physical universe and the very limits of what it means to be human. The journey toward antimatter propulsion will undoubtedly be long, fraught with setbacks, and filled with challenges that test the limits of human ingenuity. Nevertheless, the potential benefits make it one of the most compelling scientific pursuits of our era. It represents a future in which humanity can look beyond the confines of the solar system, where the nearer stars are no longer unreachable points of light, and where the energies that govern the cosmos are harnessed to propel our dreams across the vast emptiness of space. Although it remains a theoretical and highly challenging technology today, the study of antimatter propulsion continues to push forward our understanding of physics, inspire engineers, and ignite the imagination of anyone who dares to think about the stars. Every step we take toward understanding and potentially harnessing antimatter brings us closer to a future where interstellar travel is not a distant fantasy, but a tangible goal. While current limitations in production, containment, and energy management make antimatter propulsion a distant dream, ongoing research in particle physics, energy conversion, and advanced materials keeps the possibility alive. It is a pursuit that stretches the limits of human creativity and technical ability, challenging us to rethink what is possible and to innovate in ways that were previously unimaginable. The allure of near-perfect energy conversion, combined with the capacity for interstellar travel within human timescales, ensures that antimatter propulsion will remain one of the most intriguing and inspiring frontiers of space exploration for generations to come. It is this blend of extreme theoretical efficiency, overwhelming challenges, and the profound potential for discovery that makes antimatter propulsion both an object of fascination and a symbol of human ambition. The obstacles it presents, production on a massive scale, safe storage, energy control, radiation shielding, relativistic effects, and astronomical costs, are as daunting as any in the history of technology. Yet, the vision of reaching distant stars in a fraction of the time currently imaginable, of carrying humanity's hopes and dreams across light years of void, ensures that scientists, engineers, and dreamers will continue to pursue it. Antimatter propulsion embodies the ultimate synthesis of science and imagination, a quest to harness the most fundamental energies of the universe for the purpose of exploration, discovery, and the expansion of human presence across the cosmos. The idea of using light itself to move a spacecraft across the vast emptiness of space might sound like something pulled from the pages of science fiction, yet it is a concept rooted deeply in the laws of physics and has fascinated scientists and dreamers for over a century. In its essence, solar sail and laser propulsion technology relies on the simple but profound principle that light, though massless, carries momentum. When light strikes a surface, it exerts a tiny pressure, a phenomenon first measured and discussed in the early 20th century. This pressure, called radiation pressure, is exceedingly small compared to the forces we deal with on Earth, yet in the vacuum of space, where friction is almost non-existent, even the slightest push can gradually accelerate a spacecraft to remarkable speeds. The vision of using sunlight or directed lasers to propel starships is compelling, not only because it eliminates the need for carrying vast quantities of fuel, but also because it opens the door to interstellar travel in ways that traditional chemical rockets could never achieve. One of the most appealing aspects of solar sails is their simplicity and elegance. Unlike conventional rockets, which must carry fuel to push against, a solar sail needs only a large, extremely thin and reflective surface to capture the momentum of photons streaming from the sun or a powerful laser source. These sails can be made of materials so light and strong that they are almost imperceptible to the human eye, yet they cover enormous areas, sometimes hundreds of meters across. As photons strike the sail, they impart a minuscule force, gently but persistently nudging the spacecraft forward. Over weeks, months, and even years, this continuous push can gradually accelerate the spacecraft to velocities that would take chemical rockets far greater amounts of fuel and time to achieve. In space, where there is no air to slow a moving object, this steady accumulation of momentum can result in astonishing speeds, potentially allowing missions to reach nearby stars within decades rather than millennia. The concept of solar sailing is not new, and its theoretical roots can be traced back to the late 19th and early 20th centuries. Scientists and writers, intrigued by the possibilities of space exploration, began to speculate on the practical applications of light as a means of propulsion. In 1960, the idea began to transition from theory to experimentation, when engineers and physicists started designing small-scale prototypes to test in space. These early attempts were modest, but they laid the groundwork for more ambitious projects in the 21st century. By the year 2010, several successful demonstrations of solar sails had been conducted, proving that this method of propulsion could function in the harsh environment of space. These missions included the Japanese Icaros project, which deployed a sail the size of a tennis court in 2012, using sunlight to propel a spacecraft across the solar system. The Icaros mission not only demonstrated that solar sailing works, but also incorporated thin-film solar panels on the sail, allowing the craft to generate electricity while moving through space, an innovation that greatly enhanced the potential of solar-powered propulsion systems. Laser propulsion takes the concept of light-driven travel a step further, replacing or supplementing the sun's photons with highly concentrated beams of laser light directed from Earth or an orbiting station. By focusing intense laser energy on a spacecraft's reflective sail, it is possible to achieve accelerations far beyond what sunlight alone could provide. In this system, a spacecraft no longer depends solely on the natural sunlight available in the solar system, but can be propelled with incredible force over shorter distances. The idea of laser propulsion has been championed by organizations such as Breakthrough Starshot, founded in 2016, which envisioned sending gram-scale spacecraft to the nearest star system, Alpha Centauri, at up to 20% the speed of light. These small probes, equipped with light sails just a few meters wide, would be accelerated by powerful ground-based lasers, potentially reaching their destination within decades rather than centuries. Such an achievement, once thought impossible, now seems theoretically attainable thanks to advances in laser technology, materials science, and precise guidance systems. The challenges of solar sail and laser propulsion are immense, yet they are equally fascinating. Constructing sails that are both incredibly light and extremely durable requires cutting-edge materials that can withstand the harsh radiation, temperature extremes, and micrometeoroid impacts of deep space. For laser propulsion, the precision required to focus a beam on a spacecraft across millions or even billions of kilometers is staggering, demanding unprecedented control and coordination of multiple high-powered lasers. Additionally, navigating and steering a sail in space is a subtle and complex art, often requiring careful adjustments to the sail's angle relative to the incoming photons, much like a sailor adjusting a sail to catch the wind. Despite these difficulties, the potential rewards are extraordinary. Unlike chemical rockets, which quickly run out of fuel and slow down, light-driven spacecraft can continue to accelerate for months or even years, achieving speeds that could carry them far beyond the limits of our solar system. Historical experiments have shown that even modest solar sails can generate measurable thrust. In the late 20th century, small prototypes tested in orbit demonstrated that sunlight could indeed push a spacecraft. These tests, though limited in scale, provided proof of concept and valuable lessons about sail deployment, material behavior, and attitude control. By the early 21st century, solar sails had evolved into large, deployable structures capable of carrying scientific instruments or small payloads across the solar system. One notable example is the Planetary Society's Light Sail project, which successfully demonstrated solar sail propulsion in 2015. the spacecraft deployed a 4-story tall sail made of ultra-thin polyester film, which reflected sunlight and gradually altered its orbit around the Earth. This milestone not only confirmed the viability of solar sails, but also sparked renewed interest in light-based propulsion as a serious contender for long-distance space exploration. Laser propulsion, while more speculative, is built upon a foundation of both physics and emerging technologies. High-powered lasers, which were once confined to military or industrial applications, are now advancing rapidly, with the capability to produce continuous beams strong enough to propel miniature spacecraft over vast distances. By combining lightweight materials with precisely engineered reflective surfaces, these spacecraft can convert the energy from a laser into forward momentum with remarkable efficiency. The idea is that a small spacecraft, initially weighing only a few grams, could be accelerated to a significant fraction of the speed of light by a multi-megawatt laser beam over a matter of minutes or hours. Once it achieves such speeds, the probe would coast for decades through interstellar space, potentially transmitting images or data back to Earth once it reaches its destination. This combination of laser power, precision engineering, and lightweight design represents a radical departure from traditional propulsion methods, promising a new era of exploration that could take humanity to the stars. Beyond the practical applications, solar sails and laser propulsion capture the imagination because they embody a vision of travel that is clean, elegant, and sustainable. There is no need to carry tons of chemical propellant, and no harmful exhaust gases are expelled into the void. The energy driving the spacecraft comes from abundant and renewable sources, the sun or a laser powered by electricity. In a way, this approach transforms the concept of spacecraft into something closer to a cosmic sailboat, drifting and accelerating gracefully through the emptiness of space. Scientists and engineers often describe this as a gentle, continuous push, a stark contrast to the violent and explosive thrust of traditional rockets. It is a vision of space travel that harmonizes with the natural environment of the solar system, leveraging the radiation that permeates it rather than fighting against it. The physics behind solar sails is straightforward in principle, but challenging in execution. The momentum of a photon is tiny, yet when billions or trillions of photons strike a large reflective sail, the combined effect produces a measurable force. The acceleration is initially minuscule, often a fraction of a millimeter per second squared, but over time the effect accumulates. For example, a spacecraft equipped with a sail several hundred meters across could achieve speeds of tens of kilometers per second within a few months, gradually building up to hundreds of kilometers per second over years. Unlike conventional rockets, which are constrained by the amount of propellant they can carry, a solar sail's acceleration is limited primarily by the sail's surface area, reflectivity, and the intensity of the light source. In the case of laser propulsion, the acceleration can be much higher, limited by the laser power and the spacecraft's structural integrity. Navigating and controlling a solar sail requires a deep understanding of celestial mechanics and the interaction between the sail and incoming light. By tilting the sail at different angles relative to the sun, a spacecraft can change direction, slow down or speed up, much like a sailing ship tacking into the wind. This maneuverability opens the possibility of complex missions, such as exploring multiple planets or asteroids, performing flybys of distant objects, or even reaching other star systems. Advanced guidance systems, sometimes including tiny adjustable mirrors or thrusters, help maintain the desired trajectory and correct any deviations caused by micrometeoroid impacts or variations in light intensity. Despite its elegance, the practical implementation of solar sails is not without risk. Deploying a sail hundreds of meters across in the vacuum of space is a delicate operation. Any tear or crease can compromise the sail's performance, and once in motion, a sail cannot easily stop or reverse direction without sophisticated maneuvering systems. Laser propulsion introduces additional complexities, such as keeping the laser beam perfectly focused on a rapidly moving spacecraft over millions of kilometers, accounting for atmospheric distortion and ensuring that the spacecraft's material can withstand the intense energy without melting or deforming. Yet these challenges, while formidable, are not insurmountable, and ongoing research continues to bring the dream of light-propelled spacecraft closer to reality. Looking forward, the combination of solar and laser propulsion could revolutionize space travel. missions that once required decades or centuries to reach nearby stars might become feasible within human lifetimes. Scientific probes could explore distant exoplanets, study interstellar gas clouds, or photograph objects at the edge of the solar system without the limitations imposed by conventional fuel. In addition, the principles behind light-driven propulsion could inspire new approaches to energy-efficient satellite positioning, deep space exploration, and even rapid delivery of small payloads across the solar system. The excitement surrounding these technologies is not only due to their technical possibilities, but also because they represent a profound shift in our approach to moving through space, relying on natural forces and the elegance of physics rather than brute force combustion. In the grand history of space exploration, solar sails and laser propulsion stand out as a vision that blends imagination, ingenuity, and the fundamental laws of nature. From the first theoretical discussions in the late 19th century to successful demonstrations in the early 21st century, these concepts have evolved steadily, showing that even the smallest photon can be harnessed to propel humanity farther than ever before. The quiet, relentless push of light across the vacuum of space is a reminder that the universe itself can become our engine, offering possibilities that stretch the limits of both science and imagination. While challenges remain, each experiment, each technological advance, and each successful deployment of a sail brings us closer to an era in which humanity is no longer confined to the solar system, but free to drift and accelerate among the stars. The elegance of light propulsion lies not only in its scientific foundations, but also in its symbolic meaning. It represents a method of exploration that is gentle, sustainable, and aligned with the very forces that permeate the cosmos. It challenges engineers to think differently, to embrace materials science, optics, and celestial mechanics in ways that were unimaginable just a few decades ago. The notion that a spacecraft could travel for years, silently accelerating through the emptiness, powered solely by photons from the sun or a precisely aimed laser, transforms our conception of movement in space. It is a vision of interstellar exploration that is both practical and poetic, relying on the smallest quanta of light to accomplish tasks that no conventional propulsion system could manage without massive fuel reserves and prohibitive costs. As research continues, new possibilities emerge. Hybrid systems combining solar and laser propulsion could extend the range and versatility of spacecraft, enabling journeys that cover both the solar system and nearby stars. Miniaturized spacecraft equipped with advanced sensors and communication systems could travel at unprecedented speeds, transmitting data back to Earth and opening windows into regions of space previously unreachable. The continued improvement of reflective materials, high-power lasers and guidance systems promises to transform what was once purely theoretical into practical, testable, and eventually operational missions. Among the billions of stars scattered across our Milky Way galaxy, some shine closer than the rest, whispering possibilities of exploration to those who dare to imagine a voyage that spans light years. Long before humans could even conceive of leaving Earth, storytellers, philosophers, and dreamers looked at the night sky and imagined what it would be like to reach those distant suns. Today, with advancing technology, telescopes peering deeper into the cosmos, and a growing understanding of the universe, the idea of reaching other stars is no longer purely fantasy. Potential destinations beyond the solar system beckon us with both intrigue and challenge, and the stars closest to us offer the first tangible hopes for interstellar travel. Among them, Alpha Centauri, Barnard's star, and several other nearby systems present themselves as gateways to the broader galaxy, each with unique characteristics that could shape humanity's first steps into the interstellar realm. Alpha Centauri, one of the most discussed star systems in this context, is not a single star, but a collection of 3 stars bound together by gravity. The brightest of the trio is Alpha Centauri A, a star very similar to our Sun in size, temperature, and luminosity. Its companion, Alpha Centauri B, is slightly smaller and cooler, forming a gravitational dance with its larger sibling that has lasted for billions of years. Orbiting at a much greater distance is Proxima Centauri, a faint red dwarf star that quietly holds the title of being the closest known star to our solar system. Proxima Centauri is located at a distance of approximately 4.22 light-years from Earth. To put this into perspective, light, the fastest thing in the universe, takes just over 4 years to travel from Proxima Centauri to our planet. While that may seem nearly instantaneous in human terms, it represents an almost unfathomable distance when considering spacecraft travel with current technology, which is why interstellar missions remain dauntingly challenging. Proxima Centauri is particularly fascinating because it hosts at least one confirmed planet, Proxima b, which lies within the so-called habitable zone, a region where temperatures might allow liquid water to exist. The presence of this planet immediately elevates Alpha Centauri from a distant curiosity to a potential candidate for humanity's first steps beyond the solar system. Barnard's star, another close neighbour, lies about 5.96 light-years from Earth. This red dwarf star is older than our Sun, and though it is much dimmer, it captures attention due to its incredible motion relative to other stars in the sky. Named after the American astronomer Edward Emerson Barnard, who first measured its remarkable speed in 1914, Barnard's star moves so quickly against the backdrop of more distant stars that it appears to shift noticeably over decades. Astronomers have long speculated about planets orbiting Barnard's star, and evidence suggests that at least one super-Earth-sized planet might circle it. Though smaller than Earth, this potential planet could offer an environment where water might exist under the right conditions, though its star's faint glow would make it a cold and dim world compared to our own. The mere presence of such a nearby exoplanet ignites hope that the first interstellar probe might find a world worth studying in detail, even if it is inhospitable to humans at first glance. Beyond Alpha Centauri and Barnard's star, several other nearby stars spark curiosity among astronomers and visionaries alike. Wolf 359, for instance, lies just 7.8 light-years away and is also a red dwarf. Despite its closeness, it is extremely dim and invisible to the naked eye, requiring telescopes to study its properties. Lalande 21185, at 8.3 light-years, is another nearby red dwarf that has been extensively examined for potential planets. Sirius, famously known as the brightest star in our night sky, is a relatively close neighbour at 8.66 light-years. Its companion, Sirius B, is a white dwarf, the remnant of a star that has exhausted its fuel and collapsed into an incredibly dense core. Systems like these, while lacking confirmed habitable planets in most cases, help scientists understand the diversity of stars in our cosmic neighbourhood and identify targets for future exploration. Each of these stars offers a unique combination of distance, luminosity, and potential planetary companions, forming a patchwork map of destinations for our first voyages beyond the Sun. The distances to these stars illustrate the profound challenge of interstellar travel. For context, the fastest spacecraft humanity has launched, such as the Parker Solar Probe or the New Horizons mission, travel at tens of kilometers per second. Even at speeds exceeding 70 kilometers per second, a spacecraft would take tens of thousands of years to reach the nearest stars. Such staggering timescales force engineers and scientists to think creatively about propulsion, energy, and long-term sustainability. The vastness of these distances also underscores the difference between the planets of our own solar system and the stars beyond. Whereas reaching Mars can take mere months, travelling to Alpha Centauri requires traversing more than 4 light-years, a journey that would demand technology far beyond chemical rockets and conventional spacecraft. The search for exoplanets around these nearby stars has revealed a fascinating diversity of worlds. Proxima b, for instance, is roughly 1.5 times the mass of Earth and orbits Proxima Centauri, at a distance much closer than Earth orbits the Sun, due to the star's lower luminosity. This close orbit means the planet is likely tidally locked, with one side always facing its star while the other remains in perpetual darkness. Such conditions would create extreme temperature variations, with scorching heat on the star-facing side and freezing cold on the opposite. Despite these challenges, scientists speculate that a narrow band, or terminator zone, between the day and night sides could maintain temperatures suitable for liquid water, making the planet a tantalizing subject for study. Observing and understanding such worlds can teach humanity not only about the potential for life elsewhere, but also about the limits and possibilities of planetary climates and habitability in different stellar environments. Barnard's star B, the planet suspected to orbit Barnard's star, presents a different but equally intriguing scenario. Roughly 3 to 4 times the mass of Earth, it orbits its host star in about 230 days. Despite its larger size and more distant orbit compared to Proxima b, the planet receives far less energy from its dim red dwarf star, making it likely a frigid world with surface temperatures well below freezing. These extreme conditions challenge notions of habitability, but do not entirely preclude the possibility of subsurface oceans or life existing in protected niches, similar to the icy moons within our own solar system. The study of such worlds helps expand our understanding of what habitable might mean in a universe vastly different from the one we experience on Earth. Understanding these potential destinations requires more than simply knowing their distances and the characteristics of their stars and planets. Scientists employ an array of observational tools, from ground-based telescopes equipped with powerful spectrographs to space telescopes like Hubble and the James Webb Space Telescope, to study the light from these stars and discern the presence of planets. Techniques such as the radial velocity method measure the slight wobble of a star caused by the gravitational pull of orbiting planets. Transit photometry observes the tiny dimming of a star's light when a planet crosses in front of it. Both methods have revealed a remarkable number of exoplanets, including those in our closest stellar neighbours. Each new discovery not only adds potential targets for interstellar exploration, but also provides critical data for understanding planetary formation, composition, and the likelihood of life beyond Earth. The nature of the stars themselves also influences considerations for interstellar missions. Red dwarfs, such as Proxima Centauri and Barnard's star, are smaller and cooler than the Sun, with far longer lifespans that can extend into hundreds of billions of years. This longevity offers a stable environment over vast timescales, increasing the chance for life to develop and persist on orbiting planets. However, red dwarfs are often more active in terms of stellar flares, which can bombard nearby planets with high-energy radiation, potentially stripping away atmospheres and posing hazards to any life that might exist. Sun-like stars such as Alpha Centauri A provide more familiar conditions but are farther away than their closest red dwarf neighbours, introducing a trade-off between distance and habitability. Understanding these factors is crucial for prioritising targets for observation, robotic exploration, or, in the distant future, crewed missions. Humanity's longing to reach these nearby stars is intertwined with our broader desire to explore, understand, and expand beyond the confines of our home planet. Throughout history, explorers have journeyed into the unknown, navigating oceans, deserts, and mountains in search of new lands and knowledge. In the modern era, space has become the ultimate frontier, with the nearest stars representing the farthest shores we can even conceive of reaching. Missions to Alpha Centauri or Barnard's star are no longer limited to the imagination. Concepts such as Breakthrough Starshot propose sending tiny, lightweight spacecraft propelled by powerful lasers to reach a fraction of the speed of light, allowing a journey to Alpha Centauri in just over 20 years. While these missions would not carry humans, they would return images and data, providing the first direct glimpses of planets in these distant systems. Such endeavours highlight the potential for human ingenuity to bridge the enormous distances between stars and lay the groundwork for eventual crewed exploration, even if that lies many generations in the future. As scientists and engineers consider how to reach these potential destinations, they must also confront the physical and practical challenges of long-duration space travel. The immense distances involved require propulsion systems capable of sustaining high speeds over years or decades. Shielding from cosmic radiation and interstellar dust is essential to protect delicate instruments and eventually human travellers. Life support systems, energy generation, and autonomous navigation all become critical concerns. Each of these obstacles represents not only a technical problem to be solved, but also an opportunity for innovation, pushing the boundaries of human knowledge and capability. The study of nearby stars is not simply an academic exercise. It directly informs the strategies, technologies, and designs necessary for humanity's first steps into the interstellar domain. In addition to technological challenges, the cultural and philosophical significance of travelling to nearby stars is immense. These destinations are not merely points in space, but symbols of humanity's quest for knowledge, curiosity, and survival. Establishing a presence beyond our solar system would mark a profound milestone, demonstrating that humans can endure, adapt, and explore in environments vastly different from Earth. Alpha Centauri, Barnard's star, and the other nearby systems serve as tangible markers on this journey, guiding future generations in their pursuit of discovery. Each light year travelled represents a bridge between imagination and reality, between what is known and what lies beyond the veil of our current understanding. The possibility of life existing on planets around these nearby stars adds another layer of excitement and urgency. Even the faintest hints of microbial life or complex ecosystems would revolutionize humanity's understanding of biology, evolution, and the universality of life. Detecting biosignatures such as atmospheric gases produced by living organisms is a primary goal of ongoing and future telescopic missions. Proxima b, with its proximity and location in the habitable zone, represents a promising candidate for such studies. Observing seasonal changes, atmospheric composition, and potential surface features could provide clues about whether life has arisen elsewhere in the cosmos. Similarly, Barnard Star B, despite its frigid environment, may offer insights into the resilience and adaptability of life in extreme conditions. These investigations underscore the profound scientific importance of nearby stars, extending far beyond mere distance measurements or cataloguing celestial objects. Each nearby star also provides a window into the history and evolution of the galaxy. Studying their composition, age, and motion helps astronomers reconstruct the Milky Way's past, understand stellar formation, and trace the distribution of planets over cosmic time. Red dwarfs like Proxima Centauri and Barnard's Star, with lifespans far exceeding that of the Sun, offer glimpses into the distant future, showing what long-lived stars might look like billions or even hundreds of billions of years from now. Sun-like stars such as Alpha Centauri A allow comparisons with our own system, highlighting similarities and differences that inform our understanding of planetary formation and the potential for life elsewhere. Observations of these stars act as both mirrors and windows, reflecting the nature of our own solar system, while opening views to entirely different worlds and evolutionary paths. The study of nearby stars also emphasizes the importance of international collaboration. The complexity and expense of interstellar exploration demand coordinated efforts among space agencies, universities, private companies, and independent researchers worldwide. Telescopes like the Very Large Telescope in Chile, space observatories such as the James Webb Space Telescope, and ambitious initiatives like Breakthrough Starshot demonstrate the power of cooperation in pushing the limits of exploration. By pooling resources, knowledge, and expertise, humanity can maximize the chances of success in reaching and understanding these potential destinations. The combined efforts of countless scientists, engineers, and visionaries create a shared roadmap for venturing into the vast, largely uncharted space beyond the solar system. The human fascination with the stars has always been more than mere curiosity. From the earliest days of civilization, people have gazed up at the night sky, feeling both awe and longing, as if the twinkling lights above held secrets about their own place in the vast universe. This longing has grown over centuries into a profound desire to not just understand the cosmos, but to step into it, to venture beyond the familiar boundaries of our own world. The idea of leaving Earth behind, of finding a new home among the stars, is no longer confined to myths or stories. It has become a central question in the modern pursuit of space exploration. Yet, one truth stands clearly in front of every plan for interstellar travel. The journey to another star is only meaningful if we can find a world capable of supporting human life. Without another Earth-like planet to settle on, the dream of leaving our home remains a fantasy, a beautiful thought with no practical destination. The search for habitable worlds begins with a fundamental understanding of what makes Earth so uniquely suited to life as we know it. Our planet is a delicate balance of factors that together create a stable environment. It has liquid water, a protective atmosphere, a magnetic field that shields it from harmful solar radiation, and a climate system that has remained relatively stable over millions of years. These features are not common in the universe, and finding another planet that mirrors Earth's combination of conditions is no small task. Every factor matters, and even a small deviation can mean the difference between a thriving ecosystem and a barren wasteland. Scientists describe this ideal set of conditions as the habitable zone, sometimes called the Goldilocks zone, because it is not too hot, not too cold, but just right for life to exist. This zone is usually defined by the distance from a star where a planet could maintain liquid water on its surface, but true habitability requires much more than just the right temperature. Planetary composition, atmospheric density, chemical availability, and even the stability of the parent star all contribute to whether life can survive and evolve. Astronomers have long dreamed of finding planets within these habitable zones around other stars, and in recent decades the search has moved from theory to practice. With the launch of advanced telescopes and space observatories, such as the Kepler Space Telescope in the year 2009, scientists began discovering thousands of exoplanets, planets that orbit stars beyond our own sun. Each discovery brought both excitement and new questions, as researchers analysed whether any of these worlds might resemble Earth. Some exoplanets were found to be super-Earths, larger than our planet but possibly possessing rocky surfaces, while others were gas giants similar to Jupiter or Saturn, which are unlikely candidates for human habitation. Each finding refined the criteria and methods used to identify potential new homes for humanity. The challenge, however, is enormous. Even with advanced technology, most of the planets we can currently detect are hundreds or even thousands of light-years away. The sheer distances involved in interstellar travel make it clear that only a planet that is truly hospitable could justify the risks, time, and resources required to reach it. One of the most promising nearby targets for the search for another Earth is the Alpha Centauri system, which lies roughly 4.5 light-years from our Sun. This system contains 3 stars, Alpha Centauri A and B, which are Sun-like stars, and Proxima Centauri, a smaller red dwarf. In the year 2015, astronomers announced the discovery of an Earth-sized planet orbiting Proxima Centauri within its habitable zone. This finding electrified the scientific community, suggesting for the first time that a potentially habitable world exists so close to our solar system. However, proximity alone does not guarantee suitability. Proxima Centauri is an active star, frequently emitting flares and intense radiation that could strip away a planet's atmosphere or prevent life from thriving. Despite these challenges, the discovery of Proxima b, as it is called, has renewed discussions about humanity's interstellar ambitions and the technologies needed to reach even the nearest star systems. Another fascinating candidate for exploration is Barnard's star, a red dwarf located about 6 light-years from Earth. This star has long been a target for study because of its closeness and relatively quiet nature. In the year 2018, astronomers detected a planet orbiting Barnard's star that is several times the mass of Earth. While more massive planets can hold atmospheres better and maintain heat longer, there is still uncertainty about whether this world could support liquid water or an environment suitable for human life. The search for planets around stars like Barnard's star continues to expand, driven by increasingly sophisticated techniques that detect tiny wobbles in a star's motion or subtle dimming as planets pass in front of their suns. Each discovery adds another piece to the puzzle of where humans might someday travel beyond our solar system. The process of finding a truly habitable world involves more than just spotting a planet in the right distance from its star. Scientists must determine its composition, atmosphere, climate, and potential for life. This requires examining starlight filtered through a planet's atmosphere, searching for the chemical fingerprints of water, oxygen, methane, and other molecules essential to life. Even the presence of these molecules does not guarantee habitability, as planets can have conditions that make survival difficult despite favourable chemistry. For example, Venus has an atmosphere rich in carbon dioxide, but its surface temperature is hot enough to melt lead, and its air pressure is crushingly high. Mars, by contrast, has water ice and evidence of past rivers and lakes, but its thin atmosphere and harsh radiation make long-term human habitation extremely challenging. The comparison of these worlds to Earth highlights the intricate and fragile conditions needed for life, emphasizing that finding another planet capable of supporting humanity is far from simple. Beyond the technical challenges, the quest for habitable planets also underscores a deeper philosophical question. Why do humans seek to leave Earth at all? Part of the answer lies in survival. Humanity has faced countless natural disasters, from supervolcanoes and asteroid impacts to climate shifts and pandemics. While these events have shaped life on our planet, they also remind us that our existence is tied to a single world. The idea of spreading human civilization to other planets offers a form of security, ensuring that life could continue even if Earth became uninhabitable. Yet, survival alone is not the only motivation. humans are explorers by nature, driven by curiosity, imagination, and the desire to push beyond boundaries. The stars represent both a challenge and a promise, an opportunity to expand our knowledge, technology, and perspective in ways that Earth alone cannot provide. Interstellar travel, however, is not merely a matter of desire. The distances between stars are staggering. The nearest star system, Alpha Centauri, is more than 25 trillion miles away, a number almost impossible to comprehend in daily life. At the speeds achieved by current spacecraft, it would take tens of thousands of years to reach even the closest star. This reality has led scientists and engineers to explore advanced propulsion methods, including nuclear fusion drives, antimatter engines, and light sails pushed by lasers. Each concept promises higher speeds, potentially allowing travel times of decades or centuries instead of millennia. But each also presents enormous technical and engineering challenges. The idea of building spacecraft capable of sustaining human life for such long journeys adds another layer of complexity, as life support systems must function flawlessly for decades or centuries, or generations of humans must live and die in transit. Finding a habitable world is the linchpin of all these plans. Without a suitable destination, the effort and risk of interstellar travel are meaningless. A planet that cannot sustain human life would reduce the journey to a tragic voyage with no reward. Even if humans could survive in artificial habitats aboard spacecraft, long-term colonization would require a planet with resources, fertile soil, water, and a stable environment. Terraforming, the process of modifying a planet to make it habitable, is a concept frequently discussed in science fiction, but in reality, it is a monumental task requiring technologies that do not yet exist. The closer a planet is to Earth's conditions, the more feasible human colonization becomes, which is why astronomers focus so heavily on detecting Earth analogues, planets that closely resemble our own. The search for such worlds has accelerated in recent years, thanks to missions like the Transiting Exoplanet Survey Satellite, or TESS, launched in the year 2018. TESS scans the entire sky for planets by detecting tiny dips in the brightness of stars as planets cross in front of them. Its observations have already led to the discovery of hundreds of exoplanets, some within their stars' habitable zones. The James Webb Space Telescope, launched in the year 2021, has further enhanced the search, allowing scientists to study the atmospheres of distant worlds in unprecedented detail. These instruments represent the next generation of technology that may finally answer the age-old question: are we alone? And if not, where else could life exist? Even as scientists discover potential habitable planets, the question of distance looms large. The closest candidates are light years away, and while future propulsion technologies may shorten travel times dramatically, interstellar missions will likely remain multi-generational endeavours. This raises ethical and societal questions about who would travel, how societies would function in space, and what cultural and psychological impacts long journeys would have on humans. Life aboard a starship, isolated from Earth for decades or centuries, would require social structures, governance, education, and entertainment systems to maintain the well-being of travellers. Planning such a journey requires foresight, imagination, and careful consideration of both technological and human factors. Another factor to consider is the longevity and stability of the destination planet itself. Stars evolve over millions to billions of years, changing their brightness, radiation output, and habitable zones. A planet that is hospitable today may not remain so in the distant future, especially if its star is prone to sudden flares or gradual brightening. Red dwarf stars like Proxima Centauri and Barnard's star are long-lived but often highly active, while Sun-like stars offer more stability but shorter lifespans. The window of opportunity for human settlement may be limited, requiring careful selection and timing. As humans continue the search for habitable worlds, the endeavour also unites disciplines across science, technology, and philosophy. Astrophysicists calculate orbits and model atmospheres, biologists study the conditions required for life, engineers design spacecraft capable of withstanding the rigours of interstellar travel, and ethicists and policymakers consider the implications of sending humans to new worlds. This interdisciplinary effort reflects the complexity of the challenge, emphasising that finding another Earth is not just about spotting a planet with water. It is about ensuring that a new home can sustain the full richness of human life. The discoveries made so far offer hope and caution in equal measure. Planets like Proxima b, the Barnard Star candidate, and the many exoplanets detected by TESS and Kepler suggest that the universe may contain countless worlds, some of which could host life or support human settlement. Yet, the reality of interstellar distances and the fragility of life as we know it remind us that the journey will be arduous, demanding patience, innovation, and perhaps even generations of humans willing to commit their lives to exploration. The interplay between possibility and limitation fuels both scientific inquiry and human imagination, driving the pursuit of knowledge while inspiring dreams of one day standing on the surface of another world. The idea of humans creating entire habitats in space, rather than searching endlessly for another planet that could support life, is a vision that has fascinated scientists, dreamers, and engineers for decades. Humanity has long looked up at the stars, wondering whether we are alone and whether somewhere out there exists a world like our own, teeming with life and possibilities. Yet the more we explore the vast expanse of the universe, the clearer it becomes that finding a planet with conditions suitable for human life is unimaginably difficult. The distances involved are almost incomprehensible. Even the nearest star system, Alpha Centauri, is more than 4 light-years away, meaning that light, the fastest thing in the universe, takes over 4 years to travel from there to here. If we were to send a spacecraft with current technology, it would take tens of thousands of years to reach such a destination. With these staggering challenges, it becomes clear that the idea of building artificial habitats, entire worlds that we construct and control ourselves, may not just be a dream, but a necessity for the survival and growth of our species. From the very beginning, humans have shown an extraordinary ability to adapt to new environments. From the frozen expanses of the Arctic to the deserts of Africa, we have managed to make inhospitable places livable through ingenuity, technology, and sheer determination. The same principle applies to space. While no natural planet may perfectly suit our needs, we have the potential to create controlled environments where temperature, pressure, gravity, and air composition can be tailored precisely to what humans require. Artificial habitats could range from vast, rotating space stations that simulate gravity through centrifugal force to domed colonies on the surfaces of moons or asteroids, each carefully engineered to protect inhabitants from radiation, meteor impacts, and the vacuum of space. One of the earliest and most compelling concepts for artificial habitats in space was proposed by the legendary physicist and space visionary Konstantin Tsiolkovsky in the early 20th century. He imagined enormous rotating cylinders, sometimes hundreds of meters in length, spinning in the void of space to create artificial gravity. The centrifugal force generated by the rotation would allow people inside to walk, run, and live in conditions similar to those on Earth. Later, in the 1960s and 70s, scientists such as Gerard K. O'Neill expanded on this idea, envisioning massive cylindrical and toroidal, donut-shaped space colonies that could house thousands or even millions of people. These structures, often referred to as O'Neill cylinders, would be equipped with vast amounts of farmland, freshwater reservoirs, parks and cities, essentially creating entire ecosystems floating in space. Unlike a distant exoplanet that might require decades or centuries to reach, these habitats could theoretically be constructed relatively close to Earth, perhaps in orbit around our planet or the Moon, making them far more accessible and easier to maintain and supply. The concept of artificial habitats also opens up possibilities that natural planets could never offer. On Earth, life is constrained by the laws of nature, by the planet's geography, climate, and natural disasters. In space, humans could design habitats with perfect climates, tailor-made ecosystems, and even adjustable gravity. Imagine a city where the weather is always mild, rainfall is precisely measured, and the air is always clean and breathable. Imagine forests and rivers engineered to maximize beauty and sustainability. In these controlled environments, diseases could be managed more effectively, food could be grown year-round without reliance on seasons, and energy could be harnessed from the sun in ways that are far more efficient than on Earth. Unlike colonizing another planet, where humans must adapt to harsh conditions, in an artificial habitat, the environment adapts to humans. Radiation, one of the greatest threats in space, can be effectively mitigated in artificial habitats. On Earth, our planet's magnetic field and thick atmosphere protect us from cosmic rays and solar radiation. But beyond these natural shields, space is a dangerous place. For humans travelling to Mars or other distant worlds, exposure to radiation over long periods could increase the risk of cancer and other health issues. Artificial habitats can be designed with thick protective walls, water layers, or magnetic shielding to mimic Earth's protection. Advanced materials, perhaps developed in the coming decades, could further enhance safety, making life in space not only possible, but comfortable and secure. The construction of artificial habitats will undoubtedly require an enormous amount of resources, ingenuity, and cooperation. Materials might need to be harvested from the Moon, asteroids, or other celestial bodies, reducing the enormous costs of lifting supplies from Earth. Water could be extracted from ice found on the Moon or in asteroids, and sunlight could be concentrated and directed into the habitats to provide energy and warmth. Innovative recycling systems would be essential, allowing every drop of water, every molecule of oxygen, and every bit of waste to be reused efficiently. These systems would not just sustain life, they could create closed-loop ecosystems, where humans, plants, animals, and microorganisms exist in perfect balance, much like miniature versions of Earth itself. Creating artificial habitats also challenges humanity to rethink what a world truly means. We tend to think of planets as natural spheres that support life, but a habitat could redefine that concept entirely. Worlds of our own making could be designed for specific purposes: scientific research, industrial production, education, or even recreation. Cities could float in space, illuminated by carefully arranged sunlight and artificial lights that mimic the natural rhythms of day and night. Gravity could be adjusted in different zones, perhaps allowing children to play in low gravity while adults maintain normal Earth-like gravity for health. Ecosystems could be modular, with forests, lakes, and fields carefully engineered to sustain each other. The limits of imagination become the only boundaries in a world built from scratch. Another important aspect of artificial habitats is scalability. While there may be only a handful of Earth-like planets in the entire galaxy, the potential for constructing artificial habitats is essentially limitless. One cylinder can house thousands, and multiple interconnected habitats can create entire communities in space. These habitats could drift in orbit around the Sun, forming clusters that rival small cities or even nations. Populations could expand or relocate as needed, and the habitats themselves could be redesigned and upgraded over time, something impossible to do with a natural planet. In this sense, building our own worlds could allow humanity to grow beyond the constraints of a single planet, turning space itself into a canvas for civilization. The psychological and social aspects of living in artificial habitats are also fascinating. While humans have evolved to live on a single planet, the need for exploration and the drive to adapt have always been central to our nature. Space habitats would present new opportunities for culture, art, and social organization. Humans might develop new languages, customs, and technologies suited to these unique environments. Communities could form around shared work and interests, and the experience of looking out at the stars from a habitat might deepen our appreciation of the universe. Living in a constructed world could also encourage cooperation and careful planning, as the survival of the community would depend on each individual contributing to the maintenance of the habitat. Artificial habitats may also serve as stepping stones for further exploration of the cosmos. Once humans learn to live in space on a large scale, these habitats could function as bases or launch points for missions to more distant star systems. They could become centers of learning and research, allowing humanity to test new technologies, study distant celestial bodies, and expand our knowledge of the universe in a way that would be impossible from the surface of the Earth alone. A network of interconnected habitats could even serve as a backup for humanity, ensuring the survival of our species in the event of a global catastrophe on Earth. In this sense, artificial habitats are not just a way to live in space, they are a way to secure the long-term future of human civilization. The technological challenges of creating such habitats are enormous, but none of them are beyond the realm of possibility. Advances in robotics, artificial intelligence, material science, energy production, and life support systems are steadily bringing the dream closer to reality. NASA, the European Space Agency, and private companies such as SpaceX and Blue Origin are already experimenting with technologies that could one day support long-term habitation in space. Concepts like inflatable modules, advanced 3D printing in zero gravity, and autonomous construction robots are being explored, each bringing us a step closer to the day when humans will live not on Earth alone, but in carefully crafted worlds among the stars. The vision of artificial habitats also shifts our perspective on the universe itself. Instead of being passive observers, waiting for the chance discovery of a habitable world, we become active participants, shaping our environment and creating the conditions for life wherever we go. This represents a profound evolution in human thought. It is no longer enough to simply survive on one planet. We have the potential to become architects of our own destiny, designing worlds that reflect our values, needs, and imagination. The challenge is not only technical but philosophical. What kind of worlds do we wish to create, and how can we ensure that they are sustainable, ethical, and enriching for generations to come? History teaches us that humans have always risen to the challenge of transforming their environment. From the first settlements along riverbanks to the vast cities of today, we have continually reshaped the world to suit our needs. Artificial habitats in space are simply the next step in this long journey. They allow us to extend our reach beyond the limitations of Earth, to explore and inhabit regions of the cosmos that would otherwise remain inaccessible. They also remind us that survival and progress are not passive endeavours. They require vision, creativity, and courage. In the vast, dark emptiness of space, a carefully constructed habitat can become a beacon of life, innovation, and hope. One of the most compelling aspects of artificial habitats is that they provide a solution to the scarcity problem. Earth has limited space, resources, and capacity for growth. As the global population continues to expand, the strain on natural ecosystems, food production, and energy supplies becomes increasingly severe. Artificial habitats could offer relief by providing additional living space, renewable energy sources, and opportunities for sustainable agriculture in controlled environments. They could serve as experimental zones where new agricultural techniques, energy systems, and waste management strategies are tested and perfected before being applied on a planetary scale. In this sense, these habitats are not only homes in space but also laboratories for innovation that can benefit humanity as a whole. Artificial habitats also challenge our ideas about the human body and health. Living in space has profound effects on muscles, bones, and circulation. By designing habitats with adjustable gravity, humans could maintain physical health more effectively. Exercise could be integrated into daily life in creative ways, and medical technologies could be tailored to the unique conditions of space. Nutrition could be optimized, and mental health could be supported through careful design of living spaces, access to nature, and opportunities for social interaction. In short, artificial habitats offer the potential to improve life in ways that Earth itself cannot always provide, combining the best aspects of nature with the benefits of technology. One of the greatest challenges in venturing to distant worlds is time. The distances between stars are so vast that even our fastest spacecraft would take tens of thousands of years to reach even the nearest ones. Faced with this almost incomprehensible gulf of space and time, scientists and explorers have conceived an idea that might allow humans to bridge it: cryogenic sleep and suspended animation. These concepts promise to pause human life, slowing it down or temporarily halting biological processes, so that travelers can endure journeys that would otherwise span generations. Cryogenic sleep, often called cryosleep in popular culture, involves cooling the human body to extremely low temperatures to dramatically slow metabolism and preserve cells. The idea is that a human could be put into this deeply frozen state, travel across the stars, and then be revived at the journey's end as if they had merely slept a long nap. Suspended animation takes a similar approach, but it may not require freezing to such extreme temperatures. Instead, it aims to slow or temporarily stop life processes, giving the body a pause button against aging, disease, and the ravages of time. Both ideas are grounded in the understanding that time for the body does not have to match the relentless flow of time outside it. By bending the biological clock, humans could theoretically survive voyages that span decades, centuries, or even millennia. The science behind these concepts is both ancient in curiosity and modern in innovation. For centuries, humans have been fascinated with the possibility of extending life, halting death, or slowing the aging process. Early forms of suspended animation can be traced to rudimentary experiments with hypothermia, where cooling a living organism reduces its need for oxygen and slows its heart rate. Even small drops in temperature can have dramatic effects on metabolic activity. In hospitals today, therapeutic hypothermia is used to save patients after cardiac arrest, temporarily slowing their bodily functions to prevent tissue damage. These medical achievements hint at what might one day be possible for interstellar travel, suggesting that the principle of slowing life without harming it is not purely science fiction. Cryogenic sleep, however, takes this principle to an extreme. To preserve a human for decades or centuries, body temperature must be lowered to near the freezing point of liquid nitrogen, which is approximately -196 degrees Celsius. At these temperatures, cells are effectively frozen in time. Biological processes nearly stop, chemical reactions slow to a crawl, and aging halts. The challenge, however, lies in preventing ice crystals from forming within cells. These crystals could rupture delicate structures and irreparably damage organs. Researchers have developed cryoprotectants, special chemicals that allow tissues to be frozen without forming ice, creating a glass-like state called vitrification. The human body, transformed into this suspended glass, could theoretically endure centuries without change, awaiting revival when it reaches its destination. Suspended animation does not always rely on such extreme cold. Certain animals provide natural clues to how it could work in humans. Tardigrades, also known as water bears, can survive nearly complete desiccation, freezing, and intense radiation by entering a state of cryptobiosis, effectively pausing their lives until conditions improve. Frogs in Arctic regions can survive being frozen solid during winter and resume normal activity when spring arrives. Even humans have shown tiny glimpses of this potential. In emergency medicine, patients with severe trauma can sometimes be stabilized with induced hypothermia, giving doctors crucial hours to repair life-threatening injuries. These real-world examples illustrate that suspended animation is not purely imaginary. Nature itself offers proof that life can be paused under extreme conditions. The implications of successfully creating human cryogenic sleep or suspended animation are profound. Interstellar travel, once limited by the speed of spacecraft and the human lifespan, could become achievable. A ship travelling at a fraction of the speed of light could carry explorers in stasis, who would awaken at their destination with no subjective experience of the decades or centuries spent in the void. Entire generations could travel as if time had stopped, bypassing the need for complex generational ships where descendants, rather than the original travellers, complete the journey. The psychological strain of isolation, boredom, and confinement during long voyages could be eliminated. In this way, cryogenic sleep not only addresses the biological challenges of long-distance space travel, but also the mental and emotional hurdles. Despite the promise, enormous challenges remain. Freezing and reviving an entire human body without causing cellular damage or organ failure is a feat that modern science has not yet mastered. The revival process must be carefully controlled. Thawing too quickly or unevenly could cause catastrophic injuries. The effects of decades or centuries in stasis on the brain and consciousness are unknown. Would memory and personality remain intact, or could subtle shifts occur during suspended time? Ethical and philosophical questions also arise. If a person is effectively paused for centuries, what rights do they hold during that period? Who makes decisions on their behalf? The technical obstacles are mirrored by profound moral considerations, making cryogenic sleep a field that is as philosophical as it is scientific. Advances in biotechnology, nanotechnology, and material science bring hope for overcoming these challenges. Microscopic repair systems, possibly robotic or molecular, could maintain cellular integrity while in stasis, repairing minor damage and ensuring tissues remain healthy. Improved cryoprotectants may allow for safer and longer preservation, reducing the risk of ice crystal formation. Artificial intelligence and automation could manage the spacecraft, monitor vital signs, and intervene in emergencies while passengers remain in stasis. Each breakthrough brings humanity a step closer to making interstellar travel more than a dream, transforming it into a venture that could one day extend the reach of human life across the cosmos.